Just 6 numbers. Written and read by Martin Rees. Mathematical laws underpin the fabric of our universe, not just atoms, but galaxies, stars and people. The properties of atoms, their sizes and masses, how many different kinds there are, and the forces linking them together, determine the chemistry of our everyday world. The very existence of atoms depends on forces and particles deep inside them. The objects that astronomers study, planets, stars and galaxies, are controlled by the force of gravity. And everything takes place in the arena of an expanding universe, whose properties were imprinted into it at the time of the initial Big Bang. Science advances by discerning patterns and regularities in nature, so that more and more phenomena can be subsumed into categories and laws. Theorists aim to encapsulate the essence of the physical laws in a unified set of equations and a few numbers. This book describes 6 numbers that now seem specially significant. 2 of them relate to the basic forces, 2 fix the size and overall texture of our universe and determine whether it will continue forever, and 2 more fix the properties of space itself. The cosmos is so vast because there is one crucially important huge number, which I call capital N, in nature. N is equal to a billion, 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 billion. This number measures the strength of the electrical forces that hold atoms together, divided by the force of gravity between them. If N had a few less zeros, only a short-lived miniature universe could exist. No creatures could grow larger than insects, and there'd be no time for biological evolution. Another number, called E, whose value is 0.007, defines how firmly atomic nuclei bind together and how all the atoms on Earth were made. Its value controls the power from the sun, and more sensitively, how stars transmute hydrogen into all the atoms of the periodic table. Carbon and oxygen are common, whereas gold and uranium are rare because of what happens in the stars. If E were 0.006 or 0.008 instead of 0.007, we could not exist. The third cosmic number, omega, measures the amount of material in our universe, in galaxies, diffuse gas, and dark matter. Omega tells us the relative importance of gravity and expansion energy in the universe. If this ratio were too high, relative to a particular critical value, the universe would have collapsed long ago. Had it been too low, no galaxies or stars would have formed. The initial expansion speed seems to have been finely tuned. Measuring the fourth number, lambda, was the biggest scientific news of 1998. An unsuspected new force, a cosmic anti-gravity, controls the expansion of our universe, even though it has no discernible effect on scales less than 1 billion light-years. It is destined to become ever more dominant over gravity and other forces as our universe becomes ever darker and emptier. Fortunately for us, lambda is very small. Otherwise, its effect would have stopped galaxies and stars from forming, and cosmic evolution would have been stifled before it could even begin. The seeds for all cosmic structures, stars, galaxies, and clusters of galaxies, were all imprinted in the Big Bang. The fabric of our universe depends on just one number, which I call Q, which represents the ratio of 2 fundamental energies. If Q were even smaller, the universe would be inert and structureless. If Q were much larger, it would be a violent place, in which no stars or solar systems could survive, dominated by vast black holes. The 6th crucial number has been known for centuries, although it's now viewed in a new perspective. It is the number of spatial dimensions in our world, D, and equals 3. Life couldn't exist if D were 2 or 4. Time is a 4th dimension, but distinctively different from the others, in that it has a built-in arrow. We move only towards the future. Near black holes, though, space is so warped that light moves in circles and time can almost stand still. Furthermore, close to the time of the Big Bang, and on microscopic scales, space may reveal its deepest underlying structure of all, the vibrations and harmonics of objects called superstrings, which are in a 10-dimensional space-time arena. I've highlighted these 6 numbers because each plays a crucial and distinctive role in our universe, and together they determine how the universe evolves and what its internal potentialities are. These numbers constitute a recipe for a universe. If any one of them were to be untuned, there'd be no stars and no life. Is this tuning just a brute fact, a coincidence, or is it the providence of a benign creator? I take the view that it's neither of these. An infinity of other universes may well exist where the numbers are different. Most would be stillborn or sterile. We could only have emerged, and therefore we naturally now find ourselves in a universe with the right combination. It's astonishing that an expanding universe, whose starting point is so simple that it can be specified by just a few numbers, can evolve, if these numbers are suitably tuned, into our intricately structured cosmos. Let's first set the scene by viewing these structures on all scales, from atoms up to galaxies. Start by imagining a commonplace snapshot, a man and a woman, taken from a few meters away. Then imagine the same scene from successively more remote viewpoints, each 10 times further away than the previous one. The second frame shows the patch of grass on which they are reclining. The third shows they're in a public park. The fourth reveals some small buildings. The next shows a whole city, and the next but one a segment of the Earth's horizon, viewed from so high up that it is noticeably curved. 2 frames further on, we encounter the entire Earth with its biosphere seeming no more than a delicate glaze, and contrasting with the arid features of its moon. 3 more leaps show the inner solar system, the next the entire solar system. 4 frames on, a view from a few light years away, our sun looks like just one star among its neighbours. After 3 more frames, we see the billions of similar stars in the flat disk of our Milky Way, stretching for tens of thousands of light years. 3 more leaps reveal the Milky Way as a spiral galaxy, along with Andromeda. From still further, these galaxies seem just 2 among hundreds of others, outlying members of the Virgo cluster of galaxies. A further leap shows that the Virgo cluster is itself just one rather modest cluster. In the final frame, our galaxy would be a barely detectable smudge, several billion light-years distant. The series ends there. Our horizon extends no further, but it has taken 25 leaps, each by a factor of 10, to reach the limits of our observable universe, starting with the human scale of a few meters. Now imagine a set of frames zooming inward rather than outward. From less than 1 meter, we see an arm. From a few centimeters, a small patch of skin. The next frames take us into the fine texture of human tissue, and then into an individual cell. And then, at the limits of a powerful microscope, we probe the realm of individual molecules, long strings of proteins, and the double helix of DNA. The next zoom inwards reveals individual atoms. Here the fuzziness of quantum effects comes in. There is a limit to the sharpness of the pictures we can get. No real microscope can probe within the atom, where a swarm of electrons surrounds the positively charged nucleus. But substructures 100 times smaller than atomic nuclei can be probed by studying what happens when other particles, accelerated to nearly the speed of light, are crashed into them. This is the finest detail we can directly measure. We suspect, though, that the underlying structures in nature may be superstrings, or so-called quantum foam, on scales so tiny that they'd require 17 more zooms to reveal them. Our telescopes reach out to a distance bigger than a superstring, the smallest substructure within atoms, by a 60-figure number. There would be 60 frames, of which present measurements cover 43 in our zoom lens depiction of the entire natural world. The human scale is, in a numerical sense, poised midway between the masses of atoms and the masses of stars. It would take roughly as many human bodies to make up the mass of the Sun as there are atoms in each of us, between 10 to the power 28 and 10 to the 29. That's 1 followed by 28 or 29 zeros. But our Sun is just an ordinary star in a galaxy that contains 100 billion stars. There are at least as many galaxies in our observable universe as there are stars in a galaxy. More than 10 to the 78 atoms, that's 1 with 78 zeros after it, lie within range of our telescopes. Living organisms are configured into layer upon layer of complex structure. Atoms are assembled into complex molecules. These react via complex pathways in every cell and indirectly lead to the entire interconnected structure that makes up a tree, an insect, or a human. We straddle the cosmos and the microworld, intermediate in size between the Sun, 1 billion meters in diameter, and a molecule at 1 billionth of a meter. It's no coincidence that nature attains its maximum complexity on this intermediate scale. Anything larger, if it were on a habitable planet, would be vulnerable to breakage by gravity. A universe that didn't involve large numbers could never evolve a complex hierarchy of structures. It would be dull and certainly not habitable. And there must be long time spans as well. Processes in an atom may take 1/millionth of a billionth of a second to be completed, and within the nucleus things happen even faster. The complex processes that transform an embryo into blood, bone and flesh involve a succession of cell divisions coupled with differentiation, each involving thousands of intricately orchestrated regroupings of molecules. This activity never ceases as long as we eat and breathe. And our life is just one generation in humankind's evolution, itself an episode that is just one stage in the emergence of all life. The tremendous time spans involved in evolution offer a new perspective on the question, why is our universe so big? The emergence of human life on Earth has taken 4.5 billion years. Even before our Sun and its planets could form, earlier stars must have transmuted pristine hydrogen into carbon, oxygen, and the other atoms of the periodic table. That took about 10 billion years. The size of the observable universe is roughly the distance travelled by light since the Big Bang, and so the present visible universe must be around 10 billion light-years across. The very hugeness of our universe, which seems at first to signify how unimportant we are in the cosmic scheme, is actually entailed by our very existence. This isn't to say that there couldn't have been a smaller universe, only that we could not have existed in it. The expanse of cosmic space is not an extravagant superfluity. It's a consequence of the prolonged chain of events that preceded our arrival on the scene. Creatures like us require special conditions to have evolved, so the vastness of our universe shouldn't surprise us. Cosmological ideas are no longer any more fragile and evanescent than our theories about the history of the Earth. Geologists infer that the continents are drifting over the globe about as fast as your fingernails grow, and that Europe and North America were joined together 200 billion years ago. We believe them, even though such vast spans of time are hard to grasp. And some key features of our cosmic environment are now underpinned by equally firm data. The empirical support for a Big Bang, the idea that everything in our universe started as a compressed fireball far hotter than the centre of the Sun, is now as compelling as the evidence that geologists offer on our Earth's history. The most incomprehensible thing about the universe is that it is comprehensible. This is one of Einstein's best-known aphorisms, and it expresses his amazement that the laws of physics, which our minds are somehow attuned to understand, apply not just here on Earth, but also in the remotest galaxies. Newton taught us that the same force that makes atoms fall holds the moon and planets in their courses. We now know that this same force binds the galaxies, pulls some stars into black holes, and may eventually cause the Andromeda galaxy to collapse on top of us. Atoms in the most distant galaxies are identical to those we can study in our laboratories. All parts of the universe seem to be evolving in a similar way, as though they shared a common origin. Without this uniformity, cosmology would have got nowhere. There is a great cloud in the constellation of Orion, containing enough atoms to make 10,000 suns. Part of it is a glowing nebula, heated by bright blue stars. The rest is cold, dark and dusty. Within it are warm blobs, emitting no light, but generating heat can be picked up by telescopes fitted with infrared detectors. These blobs are destined to become stars, but are at present protostars, contracting under their own gravity. Each is encircled by a disk of gas and dust. These disks are not unexpected by astronomers. The dusty cloud in Orion, though denser than most of the space between the stars, is still very rarefied, and to form a star, some of this gas must contract so much that its density rises 1 billion times. Any slight spin would be amplified during this collapse, a cosmic version of the spin-up when ice skaters pull in their arms, until centrifugal forces prevent all the material from joining the star. Surplus material will be left behind, spinning around each newly formed star, and these resultant disks are the precursors of planetary systems. Dust particles in these disks will collide frequently, sticking together to build up rocky lumps. These in turn would coalesce into larger bodies which merge to make planets. Our solar system formed in this way, from a protostellar disk. Other stars form just like our Sun, and there's every reason to expect them also to be orbited by planets. Fully formed planets orbiting other stars are harder to detect than their precursor disks. A real highlight of the late 1990s was the first compelling evidence that planets are indeed common. The principle here is very simple. An observer viewing our Sun from a distance of, say, 40 light-years couldn't see any of the planets orbiting it, even with a telescope as large as the most powerful we have on Earth. Nevertheless, the existence of Jupiter, the heaviest planet, could be inferred by careful measurements of the Sun's light. This is because the Sun and Jupiter are both pivoting around their center of mass, the so-called barycenter of the solar system. The Sun is 1,047 times more massive than Jupiter, and the barycenter is closer by just that factor to the Sun's center than to Jupiter's. The Sun consequently moves about 1,000 times more slowly than Jupiter does. The Sun's actual motion is more complicated because of extra wobbles induced by the other planets, but Jupiter is much the heaviest planet and exerts the dominant effect. By analyzing the light of nearby stars very carefully, astronomers have detected small wobbles in their motion, which are induced by orbiting planets, just as Jupiter induces such motions in our Sun. The spectrum of starlight reveals patterns due to the distinctive colors emitted or absorbed by the various kinds of atom, carbon, sodium, and so forth, that stars are made of. If a star moves away from us, its light shifts towards the red end of the spectrum, as compared with the colors emitted by the same atoms in the laboratory. This is the well-known Doppler effect. If the star is approaching, there is a shift to the blue end of the spectrum. In 1995, two astronomers, Michel Mayor and Didier Queloz, discovered that the Doppler shift in 51 Pegasi, a nearby star like our Sun, was going up and down very slightly, as though it was moving in a circle, coming towards us, then going away, then coming towards us again in a regular fashion. The implied speed was about 50 meters per second. They inferred that a planet about the size of Jupiter was orbiting it, causing this star to pivot around the center of mass of the combined system. If the invisible planet were 1,000th of the star's mass, its orbital speed would be 50 kilometers per second, 1,000 times faster than the star is moving. Geoffrey Master and Paul Butler have been the champion planet hunters in the last few years. Their instruments can record wavelength shifts of less than 1 part in 100 million. They can thereby measure the Doppler effect even when the speeds are only 100 millionth of the speed of light, 3 meters per second, and they found evidence for planets around many stars. These inferred planets are all big ones, like Jupiter or Saturn, but this merely reflects the limited sensitivity of their measurements. An Earth-like planet, weighing a few hundred times less than Jupiter, would induce motions of only a few centimeters per second, and the Doppler shift would be only about 1 part in 10 billion, too small to be discerned by the techniques that have discovered the bigger planets. The high hit rate of the planet seekers suggests that there are planets around a high proportion of Sun-like stars in our galaxy. Among these billions of candidates, it would be astonishing if there were not many planets resembling the young Earth. Only in the last 5 years have we learned for sure that there are worlds in orbit around other stars. But we are still little closer to knowing whether any of them harbors anything alive. Life on Earth has occupied an immense variety of niches. The ecosystems near hot sulphurous outwellings in the deep ocean bed tell us that not even sunlight is essential. We still don't know how or when life got started. A torrid volcano is now more favoured than Darwin's warm little pond. But it could have happened deep underground, or even in dusty molecular clouds in space. Nor do we know what the odds were against it happening here on Earth, whether life's emergence is natural, or whether it involves a chain of accidents so improbable that nothing remotely like it has happened on another planet anywhere else in our galaxy. That's why it would be crucial to detect life, even in simple and vestigial forms, elsewhere in our solar system. If life has emerged twice within our solar system, this would suggest that the entire galaxy would be teeming with life. But even if we knew that primitive life was widespread, the issue of intelligent life would still remain open. We know, at least in outline, the elaborate history and the contingencies that led to our emergence here. For 1 billion years, primitive organisms exhaled oxygen, transforming the young Earth's poisonous atmosphere and clearing the way for multicellular life. The fossil record tells us that a cornucopia of swimming and creeping things evolved during the Cambrian era 550 million years ago. The next 200 million years saw the greening of the land, offering a habitat for exotic fauna. Dragonflies as big as seagulls, millipedes a metre long, scorpions and amphibians. And then came the dinosaurs. They were wiped out in the most sudden and unpredictable of all extinctions. An asteroid crashed onto Earth, causing huge tidal waves and throwing up dust that darkened the sky for years. This opened the way for the line of mammalian descent that led to humans. An extraordinary procession of species, almost all now extinct, have swum, crawled and flown through our biosphere during its long history. We are the outcome of time and chance. Nothing seems to preordain the emergence of intelligence. Indeed, some leading evolutionists believe that even if simple life were widespread in the cosmos, intelligence could be exceedingly rare. We still understand far too little to assess the odds. The amazing and fascinating complexity of biological evolution and the variety of life on Earth makes us realize that everything in the inanimate world is, in comparison, simple. And this relative simplicity is a feature of the objects that astronomers study. Things are hard to understand because they are complex, not because they are big. The challenge of fully elucidating how atoms assemble themselves, here on Earth and perhaps on other worlds, into living beings intricate enough to ponder their origins, is more daunting than anything in cosmology. For just that reason, I don't think it's presumptuous to aspire to understand our large-scale universe. Searches for extraterrestrial intelligence, SETI or SETI, are being spearheaded by scientists at the SETI Institute in Mountain View, California. The efforts have concentrated on searches for radio transmissions that could be artificial in origin. But radio is not the only conceivable channel. Narrow-beam lasers could span interstellar distances. We already have the technology, if we so wish, to proclaim our presence many light years away by either of these methods. Indeed, the combined effect of all radio transmitters, radars and so forth would in any case reveal us to any aliens with sensitive radio telescopes. We know so little about the origin and potentialities of life that it is hard to assess what method for detecting it is best. So it's sensible to be alert to all possibilities. But we should be mindful of observational selection. Even if we do discover something, we can't infer that it's typical, because our instruments and techniques restrict us to detecting a biased and incomplete selection of what may actually be out there. If there is intelligent life elsewhere, the nearest potential sites are so far away that signals would take many years in transit. But any remote beings who could communicate with us would have some concepts of mathematics and logic that paralleled our own, and they would share a knowledge of the basic particles and forces that govern our universe. Their habitat may be very different, and their biosphere even more different from ours on Earth. But they and their planet will be made of atoms just like those on Earth. For them, as for us, the most important particles will be protons and electrons. One electron orbiting a proton makes a hydrogen atom, and electric currents and radio transmitters involve streams of electrons. A proton is 1,836 times heavier than an electron, and this number, 1836, would have the same connotations to any intelligence able and motivated to transmit radio signals. All the basic forces and natural laws will be the same for them and for us. Indeed, this uniformity, without which our universe would be a far more baffling place, seems to extend to the remotest galaxies that astronomers can study. Clearly, alien beings wouldn't use meters, kilograms, or seconds, but we could exchange information about the ratios of two masses, such as the ratio of a proton and electron masses. These are pure numbers that don't depend on what units we use. As Richard Feynman noted, he could tell extraterrestrials that he was 17 billion hydrogen atoms high, and they would understand him. Some intelligences could exist with no intellectual affinity to us whatsoever, but any beings who transmitted a signal to us must have achieved some mastery over their physical surroundings. If they had any powers of reflection, they would surely share our curiosity about the cosmic genesis event from which we've all emerged. They'd be likely to be interested in how our universe is structured into stars and galaxies, how it is expanding, and its eventual destiny. They would note, as we do, that a few key numbers are crucial to our cosmic environment. 6 of these numbers determine key features of our universe: how it expands, whether planets, stars and galaxies can form, and whether there can be a chemistry propitious for evolution. Moreover, they would know that the nature of our universe is remarkably sensitive to these numbers. If you imagine setting up a universe by adjusting 6 dials, then the tuning must be precise in order to yield a universe that could harbour life. If we were establishing a discourse with intelligent beings on another planet, it would be natural to start our discourse with gravity. This force grips planets in their orbits and holds the stars together. On a still larger scale, entire galaxies, swarms of billions of stars, are governed by gravity. No substance, no kind of particle, not even light itself, escapes its grasp. It controls the expansion of the entire universe and perhaps its eventual fate. Gravity still presents deep mysteries. It's more perplexing than any of the other basic forces of nature, but it was the first force to be described in a mathematical fashion. Sir Isaac Newton told us in the 17th century that the attraction between any two objects obeys a so-called inverse square law. The force weakens in proportion to the square of the distance between the two masses. Take them twice as far away, and the attraction between them is 4 times weaker. Newton realized that the force that makes apples fall and governs a cannonball's trajectory is the same that locks the moon in its orbit around the Earth and the planets in their elliptical orbits around the Sun. Gravity acts on a grander scale in clusters of stars and in galaxies, where billions of stars are held in orbit around a central hub. In the Sun and other stars like it, there's a balance between gravity, which pulls them together, and the pressure of their hot interior, which, if gravity didn't act, would make them fly apart. In our own Earth's atmosphere, the pressure at ground level likewise balances the weight of all the air above us. Our Earth's gravity has more drastic effects on big objects than small ones. Being the right size is crucial in a biological world. Large animals aren't just blown-up versions of small ones. They're differently proportioned, with, for instance, thicker legs in relation to their height. Imagine you doubled the dimensions of an animal but kept its shape the same. Its volume and weight would become 8 times larger, not just twice as large. But the cross-section of its legs would only go up by a factor of 4, and would be too weak to support it. It would need a redesign. The bigger they are, the harder they fall. Godzillas would need legs thicker than their bodies and would not survive a fall. Mice, on the other hand, can climb vertically and are unharmed even when dropped from many times their own height. Galileo, who died in the same year that Newton was born, was the first person clearly to realize these constraints on size. He wrote, "Nor could nature make trees of immeasurable size, because their branches would eventually fall of their own weight. When bodies are diminished, their strengths do not proportionally diminish. Rather, in very small bodies, the strength grows in greater ratio, and I believe that a little dog might carry on his back 2 or 3 dogs of the same size, whereas I doubt that a horse could carry even 1 horse his size." Similar arguments to Galileo's limit the size of birds. The constraints are more stringent for hummingbirds that can hover than for albatrosses that glide, but the limits are more relaxed for floating creatures, allowing leviathans in the ocean. Despite its importance for us, our biosphere, and for the cosmos, gravity is actually amazingly feeble compared to the other forces that affect atoms. Electric charges of opposite sign attract each other. A hydrogen atom consists of a positively charged proton with a single negative electron trapped in orbit around it. Two protons would, according to Newton's laws, attract each other gravitationally, as well as exerting an electric repulsion on one another. Both these forces depend on distance in the same way. Both follow an inverse square law, and so their relative strength is measured by an important number, which I call capital N, which is the same irrespective of how widely separated the protons are. When two hydrogen atoms are bound together in a molecule, the electric force between the protons is neutralized by the two electrons. The gravitational attraction between the protons is 36 powers of 10 feebler than the electric force, and quite unmeasurable. Gravity can safely be ignored by chemists when they study how groups of atoms bond together to form molecules. How then can gravity nonetheless be dominant, pinning us to the ground and holding the planets in their courses? It's because gravity is always an attraction. If you double a mass, then you double the gravitational pull it exerts. On the other hand, electric charges can repel each other as well as attract. They can be either positive or negative. Two charges only exert twice the force of one if they are of the same sign. But any everyday object is made up of huge numbers of atoms, each made up of a positive nucleus surrounded by negative electrons, and the positive and negative charges almost exactly cancel out. But everything has the same sign of gravitational charge, and so gravity gains relative to electric forces in larger objects. The balance of electric forces is only slightly disturbed when a solid is compressed or stretched. An apple falls only when the combined gravity of all the atoms in the earth can defeat the electrical stresses in a stalk holding it to the tree. Gravity is important to us because we live on the heavy earth. Sand grains and sugar lumps are, like us, affected by the gravity of the earth. But their self-gravity, the gravitational pull that their constituent atoms exert on each other, is negligible. Self-gravity is not important in asteroids, nor in Mars's two small potato-shaped moons, Phobos and Deimos. But bodies as large as planets, and our own large moon, are not rigid enough to maintain an irregular shape. Gravity makes them nearly round. And masses above that of Jupiter get crushed by their own gravity to extraordinary densities, unless the centre gets hot enough to supply a balancing pressure, which is what happens in the Sun and other stars like it. It's because gravity is so weak that a typical star like the Sun is so massive. In any lesser aggregate, gravity could not compete with pressure, nor squeeze the material hot and dense enough to make it shine. The Sun contains about 1,000 times more mass than Jupiter. If it were cold, gravity would squeeze it 1,000,000 times denser than an ordinary solid. It would be a white dwarf, about the size of the Earth, but 330,000 times more massive. But the Sun's core actually has a temperature of 15 million degrees, thousands of times hotter than its glowing surface, and the pressure of this immensely hot gas puffs up the Sun and holds it in equilibrium. Gravity is feebler than the forces governing the microworld by the number n, about 10 to the power 36. What would happen if gravity weren't quite so weak? Imagine, for instance, a universe where gravity was only 10 to the 30 times feebler than electric forces, not 10 to the 36. Atoms and molecules would behave just as in our universe, but objects would not need to be so large before gravity became competitive with the other forces. The number of atoms needed to make a star would be 1 billion times less in this imagined universe. Planet masses would also be scaled down by 1 billion. Irrespective of whether these planets could retain steady orbits, the strength of gravity would stunt the evolutionary potential on them. In an imaginary strong gravity world, even insects would need thick legs to support them, and no animals could get much larger. Gravity would crush anything as large as ourselves. Galaxies would form much more quickly in such a universe, and would be miniaturized. Instead of the stars being widely dispersed, they would be so densely packed that close encounters would be frequent. This would in itself preclude stable planetary systems because the orbits would be disturbed by passing stars. something that fortunately is unlikely to happen in our solar system. But what would preclude a complex ecosystem even more would be the limited time available for development. Heat would leak more quickly from these mini-stars. In this hypothetical strong gravity universe, stellar lifetimes would be 1 million times shorter. Instead of living for 10 billion years, a typical star would live for about 10,000 years. A mini-sun would burn faster and would have exhausted its energy before even the first steps in organic evolution had got underway. Conditions for complex evolution would undoubtedly be less favourable if gravity were stronger. There wouldn't be such a huge gulf as there is in our actual universe between the immense time spans of astronomical processes and the basic microphysical timescales for physical or chemical reactions. It is only because gravity is weak compared with other forces that large and long-lived structures can exist. Paradoxically, the weaker gravity is, provided it isn't actually zero, the grander and more complex can be its consequences. We have no theory that tells us the value of n. All we know is that nothing as complex as humankind could have emerged if n were much less than 1 billion, 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 billion. More than 2 centuries after Newton, Einstein proposed his theory of gravity known as general relativity. According to this theory, planets actually follow the straightest path in a space-time that is curved by the presence of the sun. It's commonly claimed that Einstein overthrew Newtonian physics, but this is misleading. Newton's law still describes motion in the solar system, the most famous discrepancy being a slight anomaly in Mercury's orbit that was resolved by Einstein's theory, and is adequate for programming the trajectories of space probes to the moon and planets. Einstein's theory, however, copes, unlike Newton's, with objects whose speeds are close to that of light, with the ultra-strong gravity that could induce such enormous speeds, and with the effect of gravity on light itself. More important still, Einstein deepened our understanding of gravity. To Newton, it was a mystery why all particles fell at the same rate and followed identical orbits, why the force of gravity and the inertia were in exactly the same ratio for all substances, in contrast to electric forces where the charge and mass are not proportionate. But Einstein showed that this was a natural consequence of all bodies taking the same, straightest path in a space-time curved by mass and energy. The theory of general relativity was thus a conceptual breakthrough, especially remarkable because it stemmed from Einstein's deep insight, rather than being stimulated by any specific experiment or observation. Einstein didn't prove Newton wrong. He transcended Newton's theory by incorporating into it something more profound and with wider applicability. Einstein's achievement was to discover a set of equations that can be applied by any observer and incorporate the remarkable circumstance that the speed of light, measured in any local experiment, is the same however the observer is moving. The physicist and historian Julian Barber offers a mountaineering metaphor about the development of science which I think rings true. The higher we climb, the more comprehensive the view. Each new vantage point yields a better understanding of the interconnection of things. What is more, gradual accumulation of understanding is punctuated by sudden and startling enlargements of the horizon, as when we reach the brow of a hill and see things never conceived of in the ascent. Once we have found our bearings in a new landscape, our path to the most recently attained summit is laid bare and takes its honourable place in the new world. Experience shapes our intuition and common sense. We assimilate the physical laws that directly affect us. Newton's laws are in some sense hardwired into monkeys that swing from tree to tree. But far out in space lie environments differing hugely from our own. We should not be surprised that common sense notions break down over vast cosmic distances, or at high speeds, or when gravity is strong. An intelligence that could roam rapidly through the universe, constrained by the basic physical laws but not by current technology, would extend its intuitions about space and time to incorporate the distinctive and bizarre-seeming consequences of relativity. The speed of light turns out to have very special significance. It can be approached but never exceeded. But this cosmic speed limit imposes no bounds to how far you can travel in your lifetime, because clocks run slower and on-board time is dilated as a spaceship accelerates towards the speed of light. However, were you to travel to a star 100 light-years away and then return, more than 200 years would have passed at home, however young you still felt. Your spacecraft cannot have made the journey faster than light, as measured by a stay-at-home observer, but the closer your speed approached that of light, the less you would have aged. These effects are counterintuitive, simply because our experience is limited to slow speeds. An airliner flies at only 1/1,000,000th of the speed of light, not nearly fast enough to make the time dilation perceptible. Even for the most inveterate air traveller, it would be less than a millisecond over an entire lifetime. This tiny effect has nevertheless now been measured and found to accord with Einstein's predictions by experiments using atomic clocks accurate to 1/1000,000th of a second. A related time dilation effect is caused by gravity. Near a large mass, clocks tend to run slow. This too is almost imperceptible here on Earth because, just as we are only used to slow motions, we experience only weak gravity. This dilation must, however, be allowed for, along with the effects of orbital motion, in programming the amazingly accurate Global Positioning System, GPS. A measure of the strength of a body's gravity is the speed with which a projectile must be fired to escape its grasp. It takes 11.2 kilometers per second to escape from the Earth. This speed is tiny compared to that of light, 300,000 kilometers per second, but it challenges rocket engineers constrained to use chemical fuel, which converts only 1/1000,000th of its so-called rest mass energy into effective power. The escape velocity from the Sun's surface is 600 kilometers per second, still only 1/5 of 1% of the speed of light. Newtonian theory works with only very small corrections everywhere in our solar system. But we should prepare for surprises when gravity is far stronger. And astronomers have discovered such places. Neutron stars, for instance. Stars leave these ultra-dense remnants behind when they explode as supernovae. Neutron stars are typically 1.4 times as massive as the Sun, but only about 20 kilometers across. On their surface, the gravitational force is 1,000,000,000 times fiercer than on the Earth. A pen dropped from 1 meter above a neutron star surface would impact with the energy of a ton of TNT. A projectile would need to attain half the speed of light to escape its gravity. Conversely, anything that fell freely onto a neutron star from a great height would impact at more than half the speed of light. Newton's theory cannot cope when gravity is as powerful as it is around neutron stars. Einstein's general relativity is needed. Clocks near the surface would run 10 or 20% slower compared to those far away. Light from the surface would be strongly curved, so that viewed from afar, you would see not just one hemisphere, but part of the backside of the neutron star as well. A body that was a few times smaller or a few times heavier, even than a neutron star, would trap all the light in its vicinity and become a black hole. The space around it would close up on itself. If the Sun was squeezed down to a radius of 3 kilometers, it would become a black hole. Fortunately, nature has done such experiments for us because the cosmos is known to contain objects that have collapsed, puncturing space and cutting themselves off from the external universe. There are many millions of black holes in our galaxy of about 10 solar masses each, which are the terminal state of massive stars, or perhaps the outcome of collisions between stars. When isolated in space, such objects are inconspicuous. They can be detected only by the gravitational effect that they exert on other bodies or light rays that pass close to them. Easier to detect are those with an ordinary star orbiting around them to make a binary system. The technique for detecting them is similar to that used to infer planets from the motion they induce in their parent star. But in this case, the task is easier, because the visible star is of lower mass than the dark object, instead of being 1,000 or more times heavier, and so gyrates in a larger and faster orbit. Astronomers are always specially interested in the most extreme phenomena in the cosmos, because it's through studying these that we are most likely to learn something fundamentally new. Perhaps most remarkable of all are the amazingly intense flashes called gamma-ray bursts. These events, so powerful that for a few seconds they outshine 1,000,000 entire galaxies of stars, are probably black holes caught in the act of formation. Much larger black holes lurk in the centers of galaxies. We infer their presence by observing intense radiation from gas swirling around them at close to the speed of light, or by detecting the ultra-rapid motion of stars passing close to them. The stars very close to the center of our galaxy are orbiting very fast, as though feeling the gravity of a dark mass, a black hole with a mass of 2.5 million suns. The size of a black hole is proportionate to its mass, and the hole at the galactic center has a radius of 6 million kilometers. Some of the real monsters in the centers of other galaxies, weighing as much as several billion suns, are as big as our entire solar system, although they are nonetheless still very small compared with the galaxies in whose cores they lurk. Peculiar and counterintuitive though they are, black holes are actually simpler to describe than any other celestial object. The Earth's structure depends on its history and on what it's made of. Similarly sized planets orbiting other stars would assuredly be very different. And the Sun, basically a huge globe of gas exhibiting continuous turbulence and flaring on its surface, would look different if it contained a different mix of atoms. But a black hole loses all memory of how it was formed, and quickly settles down to a standard smooth state, described just by two quantities: how much mass went into it and how fast it's spinning. In 1963, long before there was any evidence that black holes existed, a theorist from New Zealand, Roy Kerr, discovered a solution of Einstein's equations that represented a spinning object. Later work by others led to the remarkable result that anything that collapses would settle down into a black hole that was exactly described by Kerr's formula. Black holes are as standardized as elementary particles. Einstein's theory tells us exactly how they distort space and time, and what shape their surface is. Around black holes, our intuitions about space and time go badly awry. Light travels along the straightest path, but in strongly warped space this can be a complicated curve, and near black holes time runs very slowly. Conversely, if you could hover close to a black hole, you would see the external universe speeded up. There is a well-defined surface around a black hole where, to an object at a safe distance, clocks or infalling experimenters would seem to freeze because the time dilation becomes almost infinite. Not even light can escape from inside this surface. The distortions of space and time are even worse there. It's as though space itself is being sucked in so fast that even an outwardly directed light ray is dragged inwards. In a black hole, you can no more move outwards in space than you can move backwards in time. Anyone who passes inside the surface is trapped and fated to be sucked inward towards a region where, according to Einstein's equations, gravity goes infinite within a finite time. This so-called singularity signifies the conditions transcend the physics that we know about, just as we believe they did at the very beginning of our universe. Anyone falling into a black hole thus encounters the end of time. Is this a foretaste of the big crunch that could be the ultimate fate of our universe, or does our universe have a perpetual future? Or could some still unknown physics protect us from this fate? Einstein's theory was famously triggered by his happy thought that gravity was indistinguishable from accelerated motion and would be undetectable in a freely falling lift. Non-uniformities in gravity cannot, however, be eliminated. If a phalanx of kamikaze astronauts were in free fall towards the Earth in regular formation, then the horizontal spaces between them would shrink, but the vertical spacings would increase. This is because their trajectories all converge towards the center of the Earth, and the gravitational force pulls more strongly on those lower down in the formation and hence nearer the Earth. There would be a similar effect between the different parts of each astronaut's body. Falling feet first, the astronaut would feel a vertical stretching and a sideways compression. This so-called tidal force, imperceptible for astronauts in the Earth's gravity, becomes catastrophically large in a black hole, leading to shredding and spaghettification before the central singularity is reached. There are still lively debates about exactly how black holes formed, but there is no mystery about how gravity could have overwhelmed all other forces in a dead star, or within a cloud of gas in the center of a galaxy. These formation processes require them to be at least as massive as a star, because we've seen that for asteroids and planets, gravity can't compete with other forces. The scale of stars, which determines the mass of black holes that can actually form today, stems, as we've seen, from a balance between gravity and atomic forces. But nothing in Einstein's theory picks out any special mass. Black holes are made from the fabric of space itself. Insofar as space is a smooth continuum, nothing, apart from a simple scaling, distinguishes whether a whole, once it's formed, is as big as an atom, or as big as a star, or as big as our entire universe. Even a hole that was only the size of an atom would have the mass of a mountain. Black holes are by definition objects where gravity has overwhelmed all other forces. For an atom-sized black hole to form, 10 to the power 36 atoms must be squeezed into the dimensions of 1. This forbidding requirement is another consequence of the hugeness of our cosmic number n, which measures the weakness of gravity on the atomic scale. What about black holes even smaller than an atom? Here there is an eventual limit due to an inherent graininess of space on the tiniest scale. Atomic scale black holes could have formed, if at all, only in the immense pressures that prevailed at the earliest instance of the universe. If they actually exist, such mini-holes will be extraordinary missing links between the cosmos and the microworld. The Sun is fueled by conversion of hydrogen, the simplest atom, whose nucleus consists of 1 proton, into helium, which is the second simplest nucleus, consisting of 2 protons and 2 neutrons. Attempts to harness fusion as a power source, so-called controlled fusion, have so far been stymied by the difficulty of achieving the requisite temperatures of many millions of degrees. It's even more of a problem to confine this ultra-hot gas physically in a laboratory. It would obviously melt any solid container, and it has instead to be trapped by magnetic forces. But the Sun is so massive that gravity holds down the overlying cooler layers, and thereby keeps the lid on the high-pressure core. The Sun has adjusted its structure so that nuclear power is generated in the core and diffuses outward at just the rate needed to balance the heat lost from the surface, heat that is the basis for life on Earth. This fuel has kept the Sun shining for nearly 5 billion years. But when it starts to run out, in another 5 billion years or so, the Sun's core will contract and the outer layers expand. For 100 million years, the Sun will brighten and expand into the kind of star known as a red giant, engulfing the inner planets and vaporizing any life that remains on Earth. Some of its outer layers will be blown off, but the core will then settle down as a white dwarf, shining with a dull blue glow, no brighter than a full moon today, on the parched remains of our solar system. Astrophysicists have computed what the inside of our Sun should be like, and have achieved a gratifying fit with its observed radius, brightness, temperature, and so forth. They can tell us confidently what conditions prevail in its deep interior. They can also calculate how it will evolve over the next few billion years. Obviously, these calculations can't be checked directly. We can, however, observe other stars like the Sun that are at different stages in their evolution. Having a single snapshot of each star's life is not a fatal handicap if we have a large sample, born at different times, available for study. Even among the nearby stars we can discern some that are still youngsters, no more than 1 million years old, and others in a near-terminal state. Astrophysicists can compute, just as easily as the Sun's evolution, the life cycle of a star that is half, twice, or 10 times the mass of the Sun. Smaller stars burn their fuel more slowly. In contrast, stars 10 times as heavy as the Sun shine thousands of times more brightly and consume their fuel more quickly. Their lifetimes are much shorter than the Sun's, and they expire in a more violent way, by exploding as supernovae. They become for a few weeks as bright as several billion stars. Their outer layers, blown off at 20,000 kilometers per second, form a blast wave that plows into the surrounding interstellar gas. Supernovae represent cataclysmic events in the life of the stars, involving some extreme physical processes. So supernovae naturally fascinate astronomers. But only 1 person in 10,000 is an astronomer. What possible relevance could these stellar explosions, thousands of light years away, have to all the others, whose business lies purely on the Earth's surface? The surprising answer is that they are fundamental to everyone's environment. Without them, we would never have existed. Supernovae have created the mix of atoms that the Earth is made of, and that are the building blocks for the intricate chemistry of life. Ever since Darwin, we've been aware of the evolution and selection that preceded our emergence, and of our links with the rest of the biosphere. Astronomers now trace our Earth's origin back to stars that died before the solar system formed. These ancient stars made the atoms of which we and our planets are composed. Atoms exist in nature in 92 varieties, as represented in the periodic table. The place of each atom in the table depends on the number of protons in its nucleus. The table starts with hydrogen at number 1 and goes up to uranium at number 92. The nuclei of atoms contain not only protons but neutrons, particles that weigh slightly more than a proton but have no electric charge. Uranium is the heaviest naturally occurring element. Still heavier nuclei, with charges up to 114, have been made in laboratories. These super-heavy elements are unstable to fission. Some, like plutonium, number 94 in the table, have a lifetime of thousands of years. Those numbered beyond 100 can be manufactured in experiments that collide nuclei together, but they decay after a very transient existence. When a big star's central hydrogen has all been converted into helium, the core is pulled inwards, squeezing it hotter until the helium can itself react. Helium nuclei have twice the electric charge of hydrogen, so they need to collide faster in order to overcome the fiercer electric propulsion, and this demands a higher temperature. When the helium is itself used up, the star contracts and heats up still more. Stars like the Sun never achieve hot enough cores to permit these transmutations to go very far. But the centers of heavier stars, where gravity is more powerful, reach 1 billion degrees. They release further energy via the buildup of carbon, with 6 protons, and then by a chain of transmutations into progressively heavier nuclei, oxygen, neon, sodium, silicon, and so forth. The amount of energy released when a particular nucleus forms depends on a competition between the nuclear force that glues its protons and neutrons together and the disruptive effects of electric forces between the protons. An iron nucleus, with 26 protons, is more tightly bound than any other. Energy must be added rather than being released to build up still heavier nuclei. A star therefore faces an energy crisis when its core has been transmuted into iron. The consequences of this crisis are dramatic. Once the iron core gets above a threshold size, about 1.4 solar masses, gravity gains the upper hand, and the core implodes down to the size of a neutron star. This releases enough energy to blow off the overlying material in a colossal explosion, creating a supernova. Moreover, this material has by then an onion skin structure. Hydrogen and helium are still burning in the outer regions, but the hotter inner layers have been processed further up the periodic table. The debris thrown back into space contains this mix of elements. Oxygen is the most common, followed by carbon, nitrogen, silicon, and iron. The calculated proportions, when we take account of all types of star and the various evolutionary paths they take, agree with those observed on Earth. Iron is only the 26th element in the periodic table, and at first sight the still heavier atoms might seem a problem, because it takes an input of energy to synthesize them. But the intense heat in the collapse and the blast wave that blows off the outer layers together produce small traces of the elements in the rest of the periodic table, right up to uranium at number 92. The first stars formed about 10 billion years ago from primordial material that contained only the simplest atoms. No carbon, no oxygen, and no iron. Chemistry would then have been a very dull subject. There could certainly have been no planets around these first stars. Before our Sun even formed, several generations of heavy stars could have been through their entire life cycles, transmuting pristine hydrogen into the basic building blocks of life and flinging them back into space via strong winds or explosions. Some of these atoms found themselves in an interstellar cloud resembling the Orion Nebula, where about 4.5 billion years ago a new star condensed, surrounded by a dusty disk of gas, to become our solar system. Why are carbon and oxygen so common here on Earth, but gold and uranium so rare? The answer involves stars that exploded before our Sun formed. The Earth and we ourselves are the ashes from those ancient stars. Our galaxy is like an ecosystem, recycling atoms again and again through generations of stars. The carbon, oxygen and iron atoms in the solar system are fossils from the dusty cloud from which it formed about 4.5 billion years ago. They were made by heavier stars that had already expelled processed debris by that time. These pollutants constituted only 2% of the mass. Hydrogen and helium were still overwhelmingly the dominant atoms. Heavy atoms are, however, overrepresented here on Earth because hydrogen and helium are volatile gases that escaped from all the inner planets. In contrast, the giant planet Jupiter is, like the Sun, mainly hydrogen and helium. It was formed from the cooler outer part of the disk that surrounded the newly formed Sun, and its own gravity was enough to retain these lightweight atoms. Older stars than the Sun would have formed before our galaxy had undergone so much pollution. Their surfaces should therefore be deficient in heavy elements compared to the Sun. Starlight has a complicated spectrum, in which each kind of atom imprints a distinctive set of colours. And all the heavy elements indeed do tend to be less abundant in the older stars, corroborating this general scheme of galactic evolution. Helium, in contrast, is very abundant even in the older stars, and the reason for this leads us back to the first few minutes after the Big Bang. Accounting for the proportions of the different elements is a triumph of astrophysics. Some details are still uncertain, but the essence depends on just one number, the strength of the force that binds together the particles, the protons and the neutrons, that make up an atomic nucleus. Einstein's famous equation E=mc² tells us that mass, m, is related to energy, E, via the speed of light, c. The speed of light thus has fundamental significance. It fixes a conversion factor. It tells us how much each kilogram of matter is worth in terms of energy. The only way that mass can be converted 100% into energy is if it can be brought together with an equal mass of antimatter, something that, fortunately for our survival, doesn't exist in bulk anywhere in our galaxy. Just 1 kilogram of antimatter would yield as much energy as a large electrical power station generates in 10 years. But ordinary fuels such as gasoline, or even explosives such as TNT, release only about 1/1000th of the material's rest mass energy. Such materials involve chemical reactions, which leave the nuclei of atoms unchanged and just reshuffle the orbits of their electrons and the linkages between the atoms. But the power of nuclear fusion is awesome because it is millions of times more efficient than any chemical explosion. The nucleus of a helium atom weighs 99.3% as much as the 2 protons and 2 neutrons that go to make it. The remaining 0.7% is released mainly as heat. So the fuel that powers the Sun, the hydrogen gas in its core, converts 0.007 of its mass into energy when it fuses into helium. It is essentially this number that determines how long stars can live. Further transmutations of helium all the way up to iron release only a further 0.001. The amount of energy released when simple atoms undergo nuclear fusion depends on the strength of the force that glues together the ingredients in an atomic nucleus. This force is different from the two I have discussed so far, namely gravity and electricity, because it acts only at very short range and is only effective on the scale of an atomic nucleus. We don't directly experience this force, in contrast to the way we can feel electrical and gravitational forces. Within an atomic nucleus, however, this force grips the protons and neutrons together strongly enough to combat the electrical repulsion that would otherwise make the positively charged protons fly apart. Physicists call this force the strong interaction. This strong force, the dominant force in the microworld, holds the protons in helium and heavier nuclei together so firmly that fusion is a powerful enough energy source to provide the prolonged warmth from the Sun that was the prerequisite for our emergence. Without nuclear energy, the Sun would deflate within about 10 million years. Because the force only acts at short range, it becomes less effective in the larger and heavier nuclei. This is why the nuclei heavier than iron become less tightly bound rather than more so. Nuclear forces are crucial, but how much does their exact strength matter? What would change if 0.007 were instead 0.006 or 0.008? At first sight, one might suspect it wouldn't make much difference. If it were smaller, hydrogen would be a less efficient fuel, and the Sun and stars wouldn't live so long. But this in itself wouldn't be crucial. After all, we are here already, and the Sun is still less than halfway through its life. But there turn out to be delicate effects sensitive to this number in the synthesis process that transforms hydrogen into the rest of the periodic table. The crucial first link in the chain, the build-up of helium from hydrogen, depends rather sensitively on the strength of the nuclear strong interaction force. A helium nucleus contains 2 protons, but it also contains 2 neutrons. Rather than the 4 particles being assembled in one go, a helium nucleus is built up in stages via deuterium, heavy hydrogen, which comprises a proton plus a neutron. If the nuclear glue were weaker, so that 0.007 became 0.006, a proton could not be bonded to a neutron and deuterium would not be stable. Then the path to helium formation would be closed off. We would then have a simple universe composed of hydrogen, whose atom consists of 1 proton orbited by a single electron, and no chemistry. Stars could still form in such a universe, but they would have no nuclear fuel. They would deflate and cool, ending up as dead remnants. There would be no explosions to spray the debris back into space so that new stars could form from it, and no elements would exist that could ever form rocky planets. At first sight, one might have guessed from this reasoning that an even stronger nuclear force would have been advantageous for life by making nuclear fusion more efficient. But we couldn't have existed if this number had been more than 0.008, because then no hydrogen would have survived from the Big Bang. In our actual universe, 2 protons repel each other so strongly that the nuclear strong interaction force can't bind them together without the aid of 1 or 2 neutrons, which adds to the nuclear glue, but being uncharged, exert no extra electrical repulsion. If the number were to have been 0.008, then 2 protons would have been able to bind directly together. This would have happened readily in the early universe, so that no hydrogen would remain to provide the fuel in ordinary stars, and water could never have existed. So any universe with complex chemistry requires this key number to be in the range between 0.006 and 0.008. Some specific details are even more sensitive. The English theorist Fred Hoyle stumbled on the most famous instance of fine-tuning when he was calculating exactly how carbon and oxygen were synthesized in stars. Carbon, with 6 protons and 6 neutrons in its nucleus, is made by combining 3 helium nuclei. There is negligible chance of all 3 coming together simultaneously, and so the process happens via an intermediate stage, when 2 helium nuclei combine into beryllium, with 4 protons and 4 neutrons, before combining with another helium nucleus to form carbon. Hoyle confronted the problem that this beryllium nucleus is unstable. It would decay so quickly that there seemed little chance of a 3rd helium nucleus coming along and sticking to it before it decayed. So how could carbon ever arise? It turned out that a special feature of the carbon nucleus, namely the presence of a resonance with a very particular energy, enhances the chance that beryllium will grab another helium nucleus in the brief interval before it decays. Hoyle actually predicted that this resonance would exist. He urged his experimental colleagues to measure it, and was vindicated. This seeming accident of nuclear physics allows carbon to be built up, but no similar effect enhances the next stage in the process, whereby carbon captures another helium nucleus and turns into oxygen. The crucial so-called resonance is very sensitive to the nuclear force. Even a shift by 4% would severely deplete the amount of carbon that could be made. Hoyle therefore argued that our existence would have been jeopardized by even a few percentage points change in this key number. Irrespective of how the elements were made, any change would affect the length of the periodic table. A weaker nuclear force would shift the most tightly bound nucleus, which is now iron, lower down the periodic table, and reduce below 92 the number of stable atoms. This would lead to an impoverished chemistry. Conversely, a stronger force could enhance the stability of heavy atoms. At first sight, a longer menu of different abundant atoms would seem to open the way to a more interesting and varied chemistry. But this isn't altogether obvious. For example, the English language would not be enriched in any important sense if the alphabet had more letters in it. Likewise, complex molecules can exist in endless variety, even though there are relatively few common elements. Chemistry would be duller, and complex molecules of the kind essential for life would not exist if there were no oxygen and iron, numbers 8 and 26 respectively, and especially if carbon, number 6, were not abundant. But little would be added by enhancing the number of abundant elements or by having a few extra stable elements beyond our natural 92. The actual mix of elements depends on the nuclear force. But what is remarkable is that no carbon-based biosphere could exist if this key number had been 0.006 or 0.008 rather than 0.007. I've described how the atoms of the periodic table are made, that we are stardust, or less romantically the nuclear waste, from the fuel that makes stars shine. These processes depend on the strength of the nuclear force that glues together the protons and the neutrons within the nuclei of these atoms, measured by the cosmic number 0.007 that denotes the proportion of energy released when hydrogen fuses into helium. But where did the original hydrogen atoms come from, and how did primordial material form into the first galaxies and stars? To answer these questions, we must extend our horizons in space and time, out to the extragalactic realm, and back to an era before the birth of the first stars. We shall there encounter further numbers that describe our entire universe, and discover that our emergence depended on these two being finely tuned. Stars are agglomerated into galaxies, which are the basic units that make up the universe. Our own is typical. Its 100 billion stars lie mainly in a disk, circulating around a bright inner bulge where the stars are closer together than average. Right at the centre lurks a black hole with a mass of 2.5 million suns. A light signal would take about 25,000 years to reach us from the galactic centre, and we on Earth are rather more than halfway out towards the disk's edge. From our sun's location, the other stars in the disk appear concentrated in a band across the sky, known as the Milky Way. Typical stars take more than 100 million years for a single circuit, sometimes called a galactic year, around the galactic centre. Andromeda, our galaxy's nearest major neighbour in space, is about 2 million light-years away. To an astronomer on a planet orbiting one of Andromeda's stars, our galaxy would look rather like Andromeda does to us, a disk, viewed obliquely, made of stars and gas circling around a central hub. Millions of other galaxies are visible with large telescopes. Not all are disk-like. The other important class is the so-called elliptical galaxies, in which the stars are not organized into a disk, but are swarming around in more random orbits, each feeling the gravitational pull of all the others. Galaxies are not sprinkled around randomly in space. Most are in groups or clusters held together by gravity. Our own local group, a few million light-years across, contains the Milky Way and Andromeda, together with 34 smaller galaxies. That at least was the last count. Very faint and small members of the local group are still being discovered. Gravity is pulling Andromeda towards us at about 100 kilometers per second. In about 5 billion years, these two disk galaxies may crash together. Such crashes are routine cosmic events. We see deeper in space many other galaxies that seem to be undergoing such an encounter with another. Galaxies are so vast and diffuse, and the stars are so thinly spread, that actual collisions between individual stars are exceedingly rare. Even when two galaxies crash together and merge, there will be very few stellar impacts. All that happens is that each star feels the collective gravity of everything in the other galaxy. Orbits are so distorted that the stars end up in a single chaotic swarm, rather than two separate disks. This, of course, is just what a so-called elliptical galaxy looks like, and I suspect, though the issue is still controversial, that the big elliptical galaxies were formed in this fashion. Our local group is near the edge of the Virgo cluster, an archipelago of several hundred galaxies, whose core lies about 50 million light-years away. The clusters and groups are themselves organized into still larger aggregates. The so-called Great Wall, a sheet-like array of galaxies about 200 million light-years away, is the nearest and most prominent of these giant features. Another concentration of mass, the so-called Great Attractor, exerts a gravitational force that pulls us and the entire Virgo cluster at several hundred kilometers per second. Powerful telescopes reveal galaxies out to several billion light-years. Within this far larger volume, astronomers have mapped many more clusters like Virgo, and more features like the Great Wall. But deeper surveys don't reveal any conspicuous features on still larger scales. In the words of the Harvard astronomer Robert Kirshner, we reach the end of greatness. A box whose sides are 200 billion light-years, a distance still small compared to the horizon of our observation, which is about 10 billion light-years away, is capacious enough to accommodate the larger structures and to contain a fair sample of our universe. Wherever it is placed, such a box would contain roughly the same number of galaxies grouped in a roughly similar way into clusters, filamentary structures, etc. The hierarchy of clustering doesn't continue upwards towards indefinitely large scales. Moreover, the smoothing scale in our universe is small compared to the largest distances our telescopes can probe. As an analogy, imagine you were on a ship in the middle of the ocean. A complicated pattern of waves would surround you, stretching to the horizon. But you could study the statistics of the waves because your field of view extends far enough to encompass many of them. Even the biggest waves on the ocean are far smaller than the horizon distance, and you could, in your imagination, divide what you can see into many separate patches, each large enough to be a fair sample. Cosmic structures encompass a wide range of dimensions: stars, galaxies, clusters, and superclusters. On scales less than about 1/300th of the horizon, the concentration of galaxies varies by more than a factor of 2 from place to place. On larger scales, the fluctuations are gentler, though there are a few conspicuous features like the Great Attractor. Superclusters of galaxies, to extend the ocean analogy, are like the longest conspicuous waves. The embryos of clusters and superclusters, structures stretching millions of light years across the sky, can be traced back to a time when the entire universe was of microscopic size. This is perhaps the most astonishing link between the outer space of the cosmos and the inner space of the microworld. One's first guess might be that the texture of our universe on such large scales was irrelevant to our local habitat within the solar system. It might not seem to matter whether our galaxy contained a quadrillion stars or else only a million, rather than the 100 billion that we observe, nor whether it belonged to a cluster containing millions of other galaxies rather than just a few. But a universe much rougher than ours wouldn't be hospitable to stars and planets. On the other hand, a universe that was too smooth would be blandly uninteresting. No galaxies and stars would form, and all the material would be thinly spread and amorphous. We should note another crucial consequence of the large-scale smoothness. It makes the science of cosmology possible by allowing us to define the average properties of our universe, the topography of galaxies, the statistics of the clusters, and so forth. Despite galaxies and clusters, it is still useful to think about the smoothed-out properties of the universe, just as we can describe the Earth as round, despite the complex topography of its mountains and its ocean depth. However, it would not be useful to describe the Earth as basically round if its mountains were thousands of kilometers high rather than just a few. Even more important, we can meaningfully ask whether our entire universe is static, expanding, or contracting. Galaxies are the building blocks of our universe, and by studying the light from them, we can infer how they are moving. The 100 billion stars in a typical galaxy are too faint to be seen individually. Telescopes record the total light from many stars blurred together. This light of an entire galaxy can be analyzed into a spectrum and reveals how fast it is moving, either towards us, a shift towards the blue end of the spectrum, or away from us, a shift towards the red. Perhaps the most important single fact about our universe is that the light from all distant galaxies is shifted towards the red. All, except for a few nearby galaxies in the same cluster as our own, are receding from us. Moreover, the redshift, a measure of the recession speed, is larger for the more distant galaxies. We seem to be in an expanding universe, where clusters of galaxies get more widely separated, more thinly spread through space as time goes on. The simple relation between redshift and distance is named after Edwin Hubble, who first claimed such a law in 1929. Observers on other galaxies would witness a similar expansion of distant regions away from them. The expansion is a broad brush effect. Individual galaxies, even clusters of galaxies, are not themselves expanding. Still less does the expansion affect anything more local, such as our solar system. Cosmology has only progressed because our universe, in its large-scale structure, is uniform enough to be described by the simple Hubble expansion, where all patches seem to be expanding similarly. The expansion can be envisaged locally as a Doppler effect, but on large scales, where the apparent recession is at a good fraction of the speed of light, it's better to attribute the redshift to a kind of stretching of space while the light travels through it. The amount of reddening, in other words, the amount that the wavelengths are stretched, is then equal to the amount by which the universe has expanded while the light has been travelling towards us. A non-expanding universe would actually entail even worse paradoxes than any Big Bang theory. Stars don't have infinite energy reserves. They evolve and eventually exhaust their fuel. So therefore do galaxies, which are essentially collections of stars. It's possible to date the older stars in our Milky Way and in other galaxies by comparing their properties with the outcome of computations of how stars evolve. The oldest are about 10 billion years old, entirely consistent with the view that our universe has only been expanding for a bit longer than that. If our universe were static, all galaxies must have mysteriously switched on in their present positions in a synchronized fashion about 10 billion years ago. A non-expanding universe would entail severe conceptual difficulties. The expansion almost certainly began between 10 and 15 billion years ago, 12 or 13 billion being the best guess. There are two reasons for this persistent uncertainty in the age of our universe. The exact distances to galaxies are, unlike their recession speeds, still somewhat inexact. Also, the estimate depends on how much faster or slower the expansion might have been in the past. Light travels at a finite speed, and so we see distant regions not as they are now, but as they were a long time ago. We'd expect very distant galaxies to look different from nearby ones. Their light has taken a long time on its journey, and so they were younger and less evolved when they emitted the light now reaching us. Not all the pristine gas would at that stage have condensed into stars. These evolutionary changes would be so slow that they would only be manifest over billions of years. To detect a trend, one must therefore probe galaxies so far away that their light set out several billion years ago. The Hubble Space Telescope, HST, circles the Earth far above the blurring effect of the atmosphere and has produced the sharpest pictures yet of very distant regions. The HST is so sensitive that long exposure reveals, close packed over the sky, literally hundreds of faint smudges, even within a field of view so small that it would cover less than 1/100th of the area of the full moon, and would appear as a blank patch of sky when viewed with an ordinary telescope. The faint features in these pictures, with a diversity of shapes, are 1 billion times fainter than any star we can see with the unaided eye. But each is an entire galaxy, thousands of light years in size, which appears so small and faint because of its huge distance from us. These galaxies look different from their nearby counterparts because they are being viewed when they've only recently formed. They have not yet settled down into steadily spinning disks. Some consist mainly of glowing diffuse gas, which hasn't yet fragmented into stars. Most of them appear intrinsically bluer than present-day galaxies, because massive blue stars, which would all by now have died, were still shining when the light left these distant galaxies. We are viewing these very remote galaxies at a primitive evolutionary stage, before enough time has elapsed for many stars to have completed their lives. They have as yet no complex chemistry. There's very little oxygen, carbon, etc., even to make planets. We are seeing them at a stage when the basic building blocks for planetary systems were being laid down. The most distant galaxies are so redshifted that the wavelength of the light has been stretched by more than a factor of 6. That's how much the universe must have expanded since the light set out. If the expansion had been steady, with galaxies neither accelerating nor decelerating, then when the universe was 1/6 its present scale, it would have been 1/6 its present age. The situation is actually a bit more complicated because the recession speed would not be constant. The gravitational pull that everything in the universe exerts on everything else causes deceleration, which tends to make the earlier stages of cosmic expansion relatively even shorter. But another force may be at work that tends to speed up the expansion. There is still, therefore, some uncertainty about how far back in time or how far away in space these remote galaxies actually are. The best guess would be that their light set out when the universe was around 1/10 of its present age. Cosmologists study fossils of the past, old stars, chemical elements synthesized when our galaxy was young, etc. In that respect, they're like geologists or paleontologists trying to infer how our Earth and its fauna have evolved. But cosmologists actually have an edge over other scientists who can't do experiments and depend on historical evidence. By directing their telescopes towards distant objects, cosmologists can see the evolution they claim. Populations of distant galaxies, whose light set out several billion years ago, look different from their counterparts nearby. Because of the large-scale uniformity, all parts of the universe have had similar histories. These remote galaxies should therefore, on average, look similar to the way our Milky Way, the Andromeda Galaxy and other nearby systems would have looked billions of years ago. The field of view of a telescope is a long, thin cone, extending out to the limits of vision. The objects at each distance tell us about a specific epoch in the past. As we probe greater distances, we probe further back in time, just as a borehole through successive layers of Antarctic ice can reveal the history of the Earth's climate. Just as important as the Hubble Space Telescope has been the advent of a new generation of larger telescopes on the ground. Their 8 to 10 meter mirrors offer 16 times more collecting area than the HST, and so they can collect far more light from very faint and remote galaxies. The two Keck telescopes on Mauna Kea in Hawaii were the first of these new generation instruments to come into service, but there are now several more. Most impressive of all is the Very Large Telescope, VLT, a connected cluster of 4 telescopes, each with an 8 meter mirror, constructed in the Chilean Andes. The sharpness of the images from these ground-based telescopes is limited by the blurring due to turbulence in the atmosphere, the same process that makes stars twinkle. This limit can be surmounted either by linking 2 or more telescopes together and combining the images, or by so-called adaptive optics, whereby a mirror is continually tweaked and adjusted to compensate for fluctuations in the atmosphere. These superb instruments offer snapshots of the universe right back to when the first galaxies were forming. The first stars may actually have formed even earlier, in units smaller than present-day galaxies, but which are too faint for us to see. These later agglomerated into larger structures. The rate at which gas condenses into stars is the metabolic rate of a galaxy. It seems to have peaked when the universe was about a quarter of its present age, even though the first starlight appeared much earlier. Fewer bright stars are forming now because most of the gas in mature galaxies has already been incorporated into older stars. That, at least, is a scenario that most cosmologists accept. Fleshing out the details will need more observations and a fuller understanding of how stars form. What about still earlier epochs, before any galaxies could have formed? The best evidence that everything really emerged from a dense beginning is that intergalactic space isn't completely cold. This warmth is an afterglow of creation that manifests itself as microwaves. The first detection of this cosmic microwave background, back in 1965, was the most important advance in cosmology since the discovery of the expansion of the universe. Later measurement confirmed that these microwaves have a very distinctive property. Their intensity at different wavelengths, when plotted on a graph, traces out what physicists call a black body or thermal curve. This particular curve is expected when the radiation has been brought into balance with its environment, as happens deep inside a star or in a furnace that has burned steadily for a long time. It's just what would be expected if the microwaves were indeed a relic of a fireball phase, when everything in our universe was squeezed, hot, dense and opaque. By far the most precise measurements came during the 1990s from NASA's Cosmic Background Explorer experiment, called COBE. When experimenters present their results, they conventionally draw error bars, indicating the range of uncertainty on a graph. But for the COBE data, the bars can't be exhibited because they'd be shorter than the thickness of the curve. This truly remarkable measurement, with an accuracy of 1 part in 10,000, confirms, beyond reasonable doubt, that everything in our universe, all the stuff that galaxies are now made of, was once a compressed gas, hotter than the sun's core. The present average temperature of our universe is 2.728 degrees above absolute zero. This is, of course, exceedingly cool, around minus 270 degrees centigrade. But there's a well-defined sense in which intergalactic space still contains a lot of heat. Every cubic meter contains 412 million quanta of radiation, or photons. In comparison, the average density of atoms in the universe is only about 0.2 per cubic meter. This latter number is less precisely known because we are unsure how many atoms may be in diffuse gas or dark matter, but there seem to be about 2 billion photons for every atom in the universe. During the expansion of the universe, the density of atoms and of photons both decrease, but the decrease is the same for both, and so the ratio of photons to atoms stays the same. Because this ratio of heat to matter is so large, the early universe is often referred to as a hot Big Bang. The hot early phases wouldn't have lasted long. Only for a few minutes would the temperature have exceeded 1 billion degrees. After about 500,000 years, it had cooled to 3,000 degrees, a bit cooler than the sun's surface. This marks a significant change in the expansion process. Before that time, everything was so hot that electrons were dislodged from nuclei and moved freely. But afterwards, the electrons would have slowed down enough to attach themselves to nuclei, forming neutral atoms. These atoms cannot scatter the radiation as efficiently as free electrons were able to do during the earlier and hotter stages. The primordial material would thereafter have been transparent. The fog would have lifted. The microwaves that COBE detects are relics from the era when our universe was more than 1,000 times more compressed, at 3,000 degrees rather than 2.7 degrees, and long before any galaxies came into existence. The intense radiation in the original fireball, though cooled and diluted by expansion, is still around. It fills the universe and has nowhere else to go. The often used analogy with an explosion is misleading, as it conveys the image that the Big Bang was triggered at some particular centre. But as far as we can tell, any observer, whether on Earth, on Andromeda, or on a remote galaxy, would see the same pattern of expansion. The universe may once have been squeezed to a single point, but everyone had an equal claim to have started from that point. We can't identify the origin of the expansion with any particular location in our present universe. It's also incorrect to think of the high pressure in the early universe driving the expansion. Explosions are caused by an unbalanced pressure. Bombs on Earth or supernovae in the cosmos explode because a sudden boost in internal pressure flings debris into a low-pressure environment. But in the early universe, the pressure was the same everywhere. There was no edge, no empty region outside. The primordial gas cools and dilutes, just as happens to the contents of an expanding box. The extra gravity due to the pressure and heat energy actually slows down the expansion. This is a consistent picture, but it leaves some mysteries. Above all, it offers no explanation for why the expansion occurs. The standard Big Bang theory simply postulates that everything was set up with just enough energy to go on expanding. An answer to why it is expanding at all must be sought in the still earlier stages, where we don't have such direct evidence nor such a confident understanding of the physics. According to the Big Bang theory, our universe started off hotter than the centre of a star. Why then weren't the primordial nuclei of hydrogen all transmuted into iron during the Big Bang? Remember that nuclei of iron are more tightly bound than any others, and are built up in the cores of the biggest and the hottest stars. If this had happened, no long-lived stars could have existed in our present universe, because all the available fuel would have been used up in the early fireball. A star made of vaporized iron could exist, but it would deflate within millions of years instead of billions. Fortunately, the first few minutes of the expansion didn't allow enough time for nuclear reactions to process any of the primordial material into iron, nor even into carbon, oxygen, etc. The reactions would turn about 23% of the hydrogen into helium, but apart from a trace of lithium, no elements higher up the periodic table emerged from the Big Bang itself. This primordial helium is, however, crucial, and offers a strong corroboration of the Big Bang theory. Even the oldest objects, in which pollution by carbon, oxygen and so forth is 100 times less than in the Sun, turn out to contain 23 or 24% of helium. No star, galaxy or nebula has been found where helium is less abundant than this. It seems as though the galaxy started not as pure hydrogen, but was already a mix of hydrogen and helium. Many slow-burning low-mass stars survive, which formed several billion years before our Sun, when our galaxy was young. These contain far less carbon, oxygen and iron relative to hydrogen than the Sun does, something that is, of course, natural if these atoms were expelled from massive stars and accumulated gradually over galactic history. Helium is the only element that, according to calculations, would be created prolifically in the Big Bang. This is gratifying because it explains why there is so much helium and why the helium is so uniform in its abundance. As a bonus, the Big Bang accounts for another kind of atom, deuterium, also known as heavy hydrogen. An atom of deuterium contains not just a proton, but a neutron as well, which adds extra mass but no extra charge. The existence of deuterium is otherwise a mystery, because it is destroyed rather than created in stars. As a nuclear fuel, it's easier to ignite than ordinary hydrogen, and so newly formed stars burn up any deuterium during their initial contraction before settling down into their long hydrogen-burning phases. Helium and deuterium were made when the temperature in the compressed universe was 3 billion degrees, about 1 billion times higher than it is now. But our present universe is so diffuse, around 0.2 atoms per cubic meter, that even when compressed by this huge factor, the density is still less than that of air. If we assume a present density of 0.2 atoms per cubic meter, the computed proportions of hydrogen, helium and deuterium that would emerge from the cooling fireball universe agree with observations. This is gratifying because, as we have seen, 0.2 atoms per cubic meter is indeed close to the smoothed-out density of galaxies and gas in our universe. In about 5 billion years, the Sun will die. At about the same time, the Andromeda Galaxy, our nearest big galactic neighbour, which belongs to the same cluster as our galaxy and is actually falling towards us, will crash into the Milky Way. But will our universe still be expanding? Will the distant galaxies go on moving away from us forever, or could these motions eventually reverse, so that the entire firmament eventually recollapses to a big crunch? The answer depends on the competition between gravity and the expansion energy. We know the expansion speed now, but will gravity bring it to a halt? The answer depends on how much stuff is exerting a gravitational pull. The universe will recollapse, with gravity eventually defeating the expansion, unless some other force intervenes, if the density exceeds a definite critical value. We can readily calculate what this critical density is. It amounts to about 5 atoms in each cubic meter. That doesn't seem much. Indeed, it's far closer to a perfect vacuum than experimenters on Earth could ever achieve. But our universe actually seems to be emptier still. Suppose our star, the Sun, were modelled by an orange. The Earth would then be a millimetre-sized grain, 20 metres away. To the same scale, the nearest stars would be 10,000 kilometres away. That's how thinly spread the matter is in a galaxy like ours. But galaxies are, of course, especially high concentrations of stars. If all the stars from all the galaxies were dispersed through intergalactic space, then each star would be several hundred times further from its nearest neighbour than it actually is within a typical galaxy. In our scale model, each orange would therefore be millions of kilometres from its nearest neighbour. If all the stars were dismantled and their atoms spread uniformly through our universe, we'd end up with just 1 atom in every 10 cubic metres. There's about as much again in the form of diffuse gas between the galaxies. That's a total of 0.2 atoms per cubic metre, 25 times less than the critical density of 5 atoms per cubic metre that will be needed for gravity to bring cosmic expansion to a halt. The ratio of the actual density to the critical density is a crucial number. Cosmologists denote it by the Greek letter omega. The fate of our universe depends on whether or not omega exceeds 1. At first sight, our estimate of the actual average concentration of atoms in space seems to imply that omega is only 1/25th, or 0.04, portending perpetual expansion by a wide margin. But we shouldn't jump too soon to that conclusion. We've come to realize in the last 20 years that there's a lot more in the universe than we actually see, such unseen material consisting mainly of dark stuff of unknown nature. The things that shine, galaxies, stars, and glowing gas clouds, are a small and atypical fraction of what's actually there. Most of the material in the universe, and the main contributor to omega, emits no light, nor infrared heat, nor radio waves, nor any other kind of radiation, and is consequently hard to detect. The cumulative evidence for dark matter is now almost uncontestable. The way stars and galaxies are moving suggests that something invisible must be exerting a gravitational pull on them. This is the same line of argument by which we infer the existence of a black hole when a star is seen to be orbiting around an invisible companion. It's also the reasoning used in the 19th century when the planet Neptune was inferred to exist, because the orbit of Uranus was deviated by the pull of a more distant unseen object. In our solar system, there's a balance between the tendency of gravity to make the planets fall towards the Sun and the centrifugal effect of the orbital motions. Likewise, on the far bigger scale of an entire galaxy, there's a balance between gravity, which tends to pull everything together into the centre, and the disruptive effects of motion, which, if gravity didn't act, would make the constituent stars disperse. Dark matter is inferred to exist because the observed motions are surprisingly fast, too fast to be balanced just by the gravity of the stars and gas that we see. We know how fast our Sun is circling around the central hub of our galaxy, and we can measure the speeds of stars and gas clouds in other galaxies. These speeds, especially those of outliers orbiting beyond most of the stars, are puzzlingly high. If the outermost gas and stars were feeling just the gravitational pull of what we can see, they should be escaping. These high observed speeds tell us that a heavy invisible halo surrounds big galaxies. If there weren't a lot of this dark stuff, galaxies would not be stable, but would fly apart. The beautiful pictures of disks or spirals portray what's essentially just luminous sediment held in the gravitational clutch of vast swarms of invisible objects of unknown nature. Galaxies are 10 times bigger and heavier than we used to think. The same argument applies on a larger scale to entire clusters of galaxies, each millions of light years across. To hold them together requires the gravitational pull of about 10 times more material than we actually see. There are other telltale signs of abundant dark matter. All gravitating material, whether luminous or dark, deflects light rays, and so clusters can be weighed by detecting how strongly they deviate the paths of light rays passing through them. Indeed, the deflection of starlight by the Sun's gravity, observed during the 1919 total eclipse of the Sun, famously offered an early test of relativity that propelled Einstein to worldwide celebrity. The Hubble Space Telescope has taken spectacular pictures of some clusters of galaxies lying about 1 billion light-years away. The pictures reveal a lot of faint streaks and arcs. Each is a remote galaxy, several times further away than the cluster itself, whose image is, as it were, viewed through a distorting lens. The cluster acts like a lens that focuses light passing through it. The visible galaxies in the cluster, all added together, aren't heavy enough to produce so much distortion. To bend the light so much and cause such conspicuous distortion in the images of background galaxies, the cluster must contain 10 times more mass than we see. There's nothing implausible about dark matter per se. Why should everything in the universe be shining? The challenge is to narrow down the range of candidates. The inferred dark matter emits no light, indeed no radiation of any kind we can detect. Nor does it absorb or scatter light. This means that it can't be made of dust. We know there's some dust in our galaxy because starlight is scattered and attenuated by intervening clouds. But if the dust grains cumulatively weighed enough to make up all the dark matter, they'd black out our view of any distant stars. Small, faint stars are obvious suspects for the dark matter. Stars below 8% of the Sun's mass are called brown dwarfs. They wouldn't be squeezed hot enough to ignite the nuclear fuel that keeps ordinary stars shining. Brown dwarfs have been found as a byproduct of searches for planets in orbit around brighter stars. Others, especially nearby, have been detected by their very faint emission of red light. How many brown dwarfs might we expect altogether? Theory offers little guidance. The proportions of big and small stars are determined by very complicated processes that aren't yet understood. Not even the most powerful computers can tell us what happens when an interstellar cloud condenses into a population of stars. There are several other candidates for dark matter. Cold planets moving through interstellar space, unattached to any star, could exist in vast numbers without being detected. So could comet-like lumps of frozen hydrogen. So could black holes. Brown dwarfs or comets, or even black holes, are, however, suspected to be only a minor constituent of the dark matter. This is because there are strong reasons for suspecting that the dark matter isn't made of ordinary atoms at all. This argument is based on deuterium, heavy hydrogen. We know that any deuterium we observe must have been made in the Big Bang, not in stars. The actual amount in our universe was, until recently, uncertain. But astronomers have detected a spectral imprint of deuterium, distinguishing it from ordinary hydrogen, in the light received from very distant galaxies. The observed abundance is just a trace. Only 1 atom in 50,000 is a deuterium atom. The proportion that should emerge from the Big Bang depends on how dense the universe is, and observations agree with theory if there are 0.2 hydrogen atoms in each cubic meter. This accords quite well with the actual number of atoms in objects that shine. Half are in galaxies and the other half is in intergalactic gas, but nothing much is then left over for the dark matter. If there were enough atoms to make up all the dark matter, which would imply at least 5 and perhaps 10 times more than we actually see, the concordance with theory would be shattered. This tells us something very important. The dominant dark matter is made of something that is inert as far as nuclear reactions are concerned. Exotic particles, not anything made of ordinary atoms at all, make up the main contribution to omega. The elusive particles called neutrinos are one option. They have no electric charge and hardly interact at all with ordinary atoms. Almost all neutrinos that hit the Earth go straight through. During the first second after the Big Bang, when the temperature exceeded 10 billion degrees, everything was so compressed that the reactions converting photons, quanta of radiation, into neutrinos would have been fast enough to come into balance. In consequence, the number of neutrinos left over from the cosmic fireball can be calculated. There should be hundreds of millions of neutrinos for every atom in the universe. Because neutrinos so greatly outnumber atoms, they could be the dominant dark matter even if each weighed only 100 millionth as much as an atom. Before the 1980s, almost everyone believed that neutrinos were zero rest mass particles. They would then carry energy and move at the speed of light, but their gravitational effect would be unimportant. Likewise, the photons left over from the early universe, now detected as microwave background radiation, don't now exert any significant gravitational effects. But it now seems that neutrinos may weigh something, even though it's a very tiny amount indeed, and probably too small to render them important for the dark matter. This is nonetheless a pivotal discovery about neutrinos themselves. At first sight it makes the microworld seem more complicated, but these masses may offer extra clues to the relation between neutrinos and other particles. At least we know that neutrinos exist, although we don't yet know their exact masses. But there's a long list of hypothetical particles that might exist, and if so could have survived from the Big Bang in sufficient numbers to provide the dominant contribution to omega. These particles, heavy but electrically neutral, would generally, like neutrinos, go straight through the Earth. However, a tiny proportion are likely to interact with an atom in the material they pass through. There would be only a few collisions per day within each of us, even though our bodies each contain nearly 10 to the power 29 atoms. We ourselves clearly feel nothing. However, very sensitive experiments can detect the minuscule kick or recoil when such an impact happens in a lump of silicon or similar material. The detectors must be cooled to a very low temperature and placed deep underground, so as to reduce the confusion from other kinds of event that could drown out any genuine signal from dark matter impacts. Several groups of physicists have taken up the challenge of this underground astronomy. It's delicate and tedious work, but if they succeed, they'll not only find out what our universe is mainly made of, but as a bonus, they may discover an important new kind of particle. There may well be several different kinds of dark matter. It would, for instance, be surprising if there weren't some brown dwarfs and black holes. But exotic particles seem far more likely, because of the evidence from deuterium that most dark matter isn't made up of ordinary atoms. It's embarrassing that more than 90% of the universe remains unaccounted for. Even worse when we realize that the dark matter could be made up of entities with masses ranging from 10 to the minus 33 grams for neutrinos up to 10 to the 39 grams heavy black holes, an uncertainty of more than 70 powers of 10. But I'm optimistic that if I was speaking in 5 years' time, I'd be able to report what the dark matter is. We don't yet know what types of particle might have existed in the ultra-early phases of the universe, nor how many survive. If, as I believe, the main contribution to omega comes from new kinds of particle, our cosmic modesty may have to go a stage further. We are used to the post-Copernican idea that we don't occupy a special central place in the cosmos, but we must now abandon particle chauvinism as well. The atoms that comprise our bodies, and that make up all visible stars and galaxies, are mere trace constituents of a universe whose large-scale structure is controlled by some quite different and invisible substance. We see, as it were, just the white foam on the wave crests, not the massive waves themselves. We must envisage our cosmic habitat as a dark place, made mainly of quite unknown material. Ordinary atoms seem to be a minority constituent of the universe, swamped by quite different kinds of particles surviving from the initial instance of the Big Bang. But it's actually more of a puzzle to understand why there are any atoms, why our universe isn't solely composed of dark matter. That's because to every kind of particle there is a corresponding antiparticle. Antiparticles annihilate when they encounter ordinary particles, converting their energy into radiation. No antimatter exists in bulk anywhere on Earth. Tiny amounts can be made in accelerators, where particles are crashed together with sufficient energy to make extra particle-antiparticle pairs. Antimatter would be the ideal rocket fuel. When it annihilates, its entire rest mass energy is released, compared to the fraction 0.007 for rockets powered by nuclear fusion. Antimatter can survive only if quarantined from ordinary matter. Otherwise it betrays itself by generating intense gamma rays when it annihilates. We can be sure that our entire galaxy, all its constituent stars and gas, is matter rather than antimatter. Its content is constantly being churned up and recycled by stellar births and deaths, and had it started off half matter and half antimatter, there would by now be nothing left. But on much larger scales, the mixing would be less efficient. We can't refute the conjecture that superclusters of galaxies consist alternately of matter and antimatter. So why is there a seeming bias in favour of one kind of matter? The simplest universe, one might imagine, would have started off with particles and antiparticles mixed in equal numbers. Our universe luckily wasn't like that. If it had been, then all protons would have annihilated with antiprotons during the dense early stages. It would have ended up full of radiation and dark matter, but containing no atoms, no stars, and no galaxies. So why this asymmetry? The Russian physicist Andrei Sakharov explored whether, during the cooling immediately after the Big Bang, a small asymmetry might favour particles over their antiparticles. This imbalance could create a slight excess of quarks over antiquarks, which would later translate into an excess of protons over antiprotons. Sakharov's idea obviously requires some departure from perfect symmetry between the behaviour of matter and antimatter. But evidence for such an effect, a big surprise at the time, came in 1964 from two American physicists, James Cronin and Val Fitch, who were studying the decays of an unstable particle called the K0. They found that this particle and its antiparticle weren't perfect mirror images of each other, but decayed at slightly different rates. Some slight asymmetry was built into the laws governing the decays, offering a basis for Sakharov's idea. Suppose that for every billion particle-antiparticle pairs, such an asymmetry had led to one extra particle. As the universe cooled, particle pairs would all annihilate, eventually giving quanta of radiation. This radiation, now cooled to very low energies, constitutes the 2.7 degree background heat pervading intergalactic space. But for every billion particles that were annihilated with antiparticles, one would survive, because it couldn't find a partner to annihilate with. There are indeed more than 1 billion times more radiation quanta, photons, in the universe than there are protons. So all the atoms in the universe could result from a tiny bias in favour of matter over antimatter. We and the visible universe around us may exist only because of a difference in the 9th decimal place between the numbers of quarks and of antiquarks. Omega may not be exactly 1, but it is now at least 0.3. At first sight, this may not seem to indicate fine-tuning. However, it implies that omega was very close indeed to unity in earlier eras. This is because, unless expansion energy and gravitational energy are in exact balance, in which case omega is and remains exactly equal to unity, the gap between these two energies widens. If omega were to start off slightly less than unity in the early universe, then eventually kinetic energy would completely dominate, so that omega becomes very small indeed. On the other hand, if omega was substantially more than unity, then gravity would soon get the upper hand and bring the expansion to a halt. So this highlights a basic mystery. Why is our universe still, after 10 billion years, expanding with the value of omega not too different from unity? There are, as we've seen, good grounds for extrapolating back to when the universe was 1 second old and at a temperature of 10 billion degrees. Suppose you were setting up a universe then. The trajectory it would follow would depend on the impetus it was given. If it was started too fast, then the expansion energy would, early on, have become so dominant. In other words, omega would have become so small that galaxies and stars would never have been able to pull themselves together via gravity and condense out. The universe would expand forever, but there would be no chance of life. On the other hand, the expansion must not have been too slow, otherwise the universe would have recollapsed too soon to a big crunch. Any emergent complexity must feed on non-uniformities in density and in temperature. Our own biosphere, for example, energizes itself by absorbing the sun's hot radiation and re-emitting it into cold interstellar space. So without being anthropocentric in our concept of life, we can conclude that a universe has to expand out of its fireball state and at least cool down below 3,000 degrees before any life can begin. If the initial expansion were too slow to permit this, there would be no chance for life. In this perspective, it looks surprising that our universe was initiated with a very fine-tuned impetus, almost exactly enough to balance the decelerating tendency of gravity. It's like sitting at the bottom of a well and throwing up a stone so it comes to a halt exactly at the top. The required precision is astonishing. At 1 second after the Big Bang, omega cannot have differed from unity by more than 1 part in a million billion. We have already noted that any complex cosmos must incorporate a large number, n, reflecting the weakness of gravity. It must also have a value of the nuclear forces that allows nuclear and chemical processes to take place. But these conditions, though necessary, are not sufficient. Only a universe with a finely tuned expansion rate can provide the arena for these processes to unfold. So omega must be added to our list of crucial numbers. It had to be tuned amazingly close to unity in the early universe. If expansion was too fast, gravity could never pull regions together to make stars or galaxies. If the initial impetus were insufficient, a premature big crunch would quench evolution when it had barely begun. Our universe contains more mass in dark matter than in ordinary atoms, but is there enough to provide the full critical density, to make omega exactly equal to unity? The inferred amount within galaxies and clusters falls short of this. However, dark matter uniformly spread through the universe would not influence the internal motions within clusters, nor the light bending due to clusters, which magnifies and distorts the images of very distant galaxies. It would therefore be even more elusive. The extra material would only betray its presence by affecting the overall cosmic expansion. Can we therefore discover how this expansion rate is changing? This is certainly possible in principle. The redshift of a distant object tells us how it was moving when its light set out, as opposed to how it is moving now. By observing the redshifts and distances of a remote population of galaxies, we can infer the expansion rate at an earlier era. Comparison with the present rate then tells us how much, if at all, the expansion rate has been changing. Any change in the expansion rate would be so gradual that it would only show up over a baseline of several billion years. So there's no hope of detecting it unless we can observe objects several billion light years away. This isn't in itself an impediment, because superbly instrumented telescopes with 10-meter mirrors are now probing back to when the universe was no more than a tenth its present age. More serious is the problem of finding distant objects that are sufficiently standardized and allowing for the possibility that they look intrinsically different from their nearby counterparts because they're being observed at an earlier stage in their evolution. Galaxies are too complicated, too varied, and still too poorly understood to serve as standard candles. They are far less well understood than individual stars, but single stars are far too faint to be detected at cosmological distances. But some stars in their death throes explode as supernovae, and for a few days blaze nearly as brightly as a whole galaxy. A distinctive type of supernova, technically known as a Type 1a, signals a sudden nuclear explosion in the center of a dying star, when its burnt-out core gets above a particular threshold of mass and becomes unstable. It is then, in effect, a nuclear bomb with a standard yield. What's important is that Type 1a supernovae can be regarded as standard candles, bright enough to be detected at great distances. From how bright they appear, it should be possible to infer reliable distances, and therefore, by measuring the redshift as well, to relate the expansion speed and distance at a past epoch. Cosmologists hoped that such measurements would distinguish between a small slowdown rate, expected if the dark matter has all been accounted for, or the larger rate, expected if, as many theories suspected, there was enough extra dark matter to make up the full critical density, so that the universe resembled the simplest theoretical model. 2 teams dedicated themselves to the supernova cosmology project, and by 1998, each had discovered about a dozen distant supernovae and mustered enough confidence to announce provisional results. There was less deceleration than would have been expected if omega were equal to 1. This in itself wasn't surprising. There was no evidence for enough dark matter to raise omega above around 0.3, though it went against a strong theoretical prejudice that the cosmos would be simpler if omega were exactly unity. But what was a surprise was that there seemed no deceleration at all. Indeed, the expansion seemed to be speeding up. These observations are right at the limit of what is possible with existing telescopes, but cross-checks are being made, and every month more supernovae are added to the sample. An acceleration in the cosmic expansion implies something remarkable and unexpected about space itself. There must be an extra force that causes a cosmic repulsion, even in a vacuum. This force would be indiscernible in the solar system, nor would it have any effect within our galaxy, but it could overwhelm gravity in the still more rarefied environment of intergalactic space. Despite the gravitational pull of the dark matter, which acting alone would cause a gradual deceleration, the expansion could then actually be speeding up, and we would have to add another crucial number to our list to describe the strength of this anti-gravity. We normally think of the vacuum as nothing, but if one were to remove from a region of interstellar space the few particles that it contains, and even shield it from the radiation passing through it, and cool it to absolute zero, the emptiness that's left may still exert some residual force. Einstein projected this as early as 1917, thinking about how his theory of general relativity might apply to the universe. Einstein found that a universe in a static state would immediately start to contract, because everything in it attracts everything else. A universe couldn't persist in a static state unless an extra force counteracted gravity. So he added to his theory a new number, which he called the cosmological constant, and denoted by the Greek letter lambda. Einstein's equations then allowed a static universe, where, for a suitable value of lambda, a cosmic repulsion exactly balanced gravity. This universe was finite but unbounded. Any light beam that you transmitted would eventually return and hit the back of your head. This so-called Einstein universe became no more than a curiosity after 1929. Astronomers had by then realized that our galaxy was just one of many, and that distant galaxies were receding from us. The universe wasn't static, but was expanding. Einstein thereafter lost interest in lambda. Indeed, George Gamoff's autobiography, My World Line, recalls a conversation in which Einstein, 3 years before his death, rated lambda as his biggest blunder, because if he hadn't introduced it, his equations would have obligated the conclusion that our universe would be expanding or contracting. He could then maybe have predicted the expansion before Edwin Hubble discovered it. Einstein's reason for inventing lambda has been obsolete for 70 years. But that doesn't discredit the concept itself. On the contrary, lambda now seems less contrived than Einstein thought it was. Empty space, we now realize, is anything but simple. All kinds of particles are latent in it. Any particle, together with its antiparticle, can be created by a suitable concentration of energy. On an even tinier scale, empty space may be a seething tangle of strings, manifesting structures in extra dimensions. From our modern perspective, the puzzle is, why is lambda so small? Why don't all the complicated processes that are going on, even in empty space, have a net effect that is much larger? Why isn't space as dense as an atomic nucleus or a neutron star, in which case it would close up on itself within 10 or 20 kilometers? The case for a non-zero lambda at the present time is strong but not overwhelming. Gravity is the dominant force in planets, stars and galaxies, but on a still larger scale of the universe itself, the average density is so low that a different force may take over. The cosmic number lambda, describing the weakest force in nature as well as the most mysterious, seems to control the universe's expansion and its eventual fate. Einstein's blunder may prove a triumphant insight after all. If lambda isn't zero, we are confronted with the problem of why it has the value we observe, one smaller by very many powers of 10 than what seems its natural value. However, a much higher value of lambda would have had catastrophic consequences. Instead of becoming competitive with gravity only after galaxies have formed, A higher valued lambda would have overwhelmed gravity earlier on, during the higher density stages. If lambda started to dominate before galaxies had condensed out from the expanding universe, or if it provided a repulsion strong enough to disrupt them, then there would be no galaxies. So our existence requires that lambda should not have been too large. The elaborately structured cosmic environment that we see around us is not completely ordered, nor has it run down to an utterly random state. There are 92 different kinds of atoms in nature, rather than just the simple hydrogen, deuterium and helium that were forged in the Big Bang. Some of these atoms now find themselves in complex organisms in our Earth's biosphere, some are in stars, others are dispersed in the voids of intergalactic space. And the temperature contrasts are also immense. The stars have blazing surfaces and still hotter centers, but the dark sky is close to the absolute zero of temperature, warmed to just 2.7 degrees by the microwave afterglow from the Big Bang. That this intricate complexity all emerged from a boringly amorphous fireball might seem to violate a hallowed physical principle, the second law of thermodynamics. This law describes an inexorable tendency towards uniformity and away from patterns and structure. Things tend to cool if they are hot and to warm up if they are cold. Ink and water can readily mix, whereas the reverse process, stirring a murky liquid until the dye concentrates into a black drop, would astonish us. Ordered states get messed up, but not the reverse. In technical jargon, entropy can never decrease. An apparent decrease locally is always outweighed by an entropy increase elsewhere. The classic example of this principle is a steam engine, where the ordered motion of a piston is always accompanied by wasted heat. We need to rethink our intuitions, however, when gravity comes into play. Stars, for instance, are held together by the inward pull of their own gravity. This is balanced by the pressure of their hot interiors pushing out. Odd though it seems, stars heat up when they lose energy. Suppose that the fuel supply in the sun's center was switched off. Its surface would stay bright because heat diffuses from the even hotter core. If nuclear fusion didn't regenerate this heat, the sun would gradually deflate as energy leaked away within about 10 million years. But this deflation would actually make the core hotter than before. Gravity pulls more strongly at shorter distances, and the central temperature would have to rise in order to provide enough pressure to balance the greater force pressing down on it. So it should not surprise us that new stars condense within irregular clouds of cool, dusty gas. The densest regions contract because of their own gravity, becoming so compressed that they light up as stars. Exactly how this happens is still too hard to calculate, even with the biggest computers. But star formation poses no mystery in principle. Once gravity gets a grip on a system, it inexorably contracts. The gas clouds within our galaxy have been churned and recycled so much that they retain no memory of their origins. Star formation is therefore insensitive to the wider cosmos. But the emergence of the galaxies themselves is less straightforward than the equivalent process for stars. Their origin lies in the early universe. They are shaped by their genetics as well as by their environment. If our universe had started off completely smooth and uniform, it would have remained so throughout its expansion. After 10 billion years, it would contain thinly spread dark matter and hydrogen and helium gas so rarefied that there was less than one atom in each cubic meter. It would be cold and dull, no galaxies, therefore no stars, no periodic table, no complexity, certainly no people. But even very slight irregularities in the early phases make a crucial difference, because density contrasts amplify during the expansion. Any patch slightly denser than average decelerates more because it feels extra gravity. Its expansion lags further and further behind that of an average region. So gravity amplifies slight ripples in an almost featureless fireball, enhancing the density contrasts until the overdense regions stop expanding and condense into structures held together by gravity. The most conspicuous structures in the cosmos, stars, galaxies and clusters of galaxies, are all held together by gravity. We can express how tightly they are bound together, or equivalently how much energy will be needed to break up and disperse them, as a proportion of their total rest mass energy. For the bigger structures in our universe, clusters and superclusters, the answer is about 1 part in 100,000. This is a pure number, a ratio of two energies, and we call it Q. The fact that Q is so small, of the order 10 to the minus 5, means that gravity is actually quite weak in galaxies and clusters. Newton's theory is therefore good enough for describing how the stars move within a galaxy and how each galaxy traces out an orbit under the gravitational influence of all the other galaxies and the dark matter within a cluster. The smallness of Q also means that we can validly treat our universe as approximately homogeneous, just as we'd regard a globe as smooth and round if the height of the waves or ripples on its surface were only 100,000th of its radius, equivalent to only 60 meters for a globe the size of the Earth. The number Q is crucial for determining the texture of structure in our universe, which would be very different if its value were either much larger or much smaller. Our universe started off dense and opaque, like the glowing gas inside a star. But after 500,000 years of expansion, the temperature had dropped to around 3,000 degrees, slightly cooler than the sun's surface. As the universe cooled further, it literally entered a dark age. The darkness persisted until the first proto-galaxies formed and lit it up again. The microwave background radiation, the afterglow from the Big Bang itself, is a direct message from an era when galaxies only existed in embryo. Slightly overdense regions, expanding slower than average, were destined to become galaxies or clusters. Others, slightly underdense, were destined to become voids. And the microwave temperature should bear the imprint of these fluctuations. The expected effect would be about 1 part in 100,000, essentially the same number as Q, the fundamental number characterizing the ripple amplitude. An undoubted cosmological triumph of the 1990s was the actual mapping of these precursors of cosmic structure. The background microwave radiation is about 100 times weaker than the emission from the Earth, whose surface temperature is about 300 degrees above absolute zero. The daunting technical challenge is to measure temperature differences 100,000 times smaller still. NASA's COBE satellite carried the first instruments sensitive enough to discern that the radiation from some directions was slightly hotter than from others. It scanned the whole sky, measuring the temperature with enough precision to map its non-uniformities. It was actually a relief to find these non-uniformities in the afterglow temperature at a level of 1 part in 100,000. If the background microwaves had implied an even smoother early universe, the clusters and superclusters in our present universe would have been a puzzle. There would need to have been some extra force, apart from gravity, that could enhance the density contrast even faster. But the fact that Q is only 1 over 100,000, 10 to the minus 5, is really the most remarkable feature of our universe. If you picked up a stone that was spherical to a precision of 1 part in 100,000, you might wonder what caused the small irregularities, but you'd be even more perplexed by the overall smoothness. Inflation, described later, is the best theory we have of this, and the temperature fluctuations offer important tests of these ideas. When the universe was 1 million years old, everything was still expanding almost uniformly. How did the structures condense out and develop into the cosmic scene we now observe? Nowadays, we can use a computer to study virtual universes. At the start of the simulation, the material is expanding, but not quite uniformly, because irregularities are fed in as part of the initial conditions. Cosmic structure forms hierarchically, from the bottom up. Swarms of dark matter on subgalactic scales condense out first. These merge into galactic mass objects, which then form clusters. It takes longer for gravity to reverse the expansion on larger scales. The first condensations to form, those that would cause the first light that ends the cosmic dark age, are 1 million times heavier than stars. These first objects would have formed when the universe was only a few 100 million years old, a few % of its present age. By the time the universe was 1 billion years old, galaxy-sized structures would have built up, each an assemblage of stars held together not only by its own gravity, but by the dark matter, which is configured in a swarm 10 times larger and heavier. Gas continues to fall inward into these objects and to cool down. If it is spinning, the gas settles into a disk and condenses into stars, thereby initiating the recycling process that synthesizes and disperses all the elements of the periodic table. Computer simulations that show at least the broad outline of these processes can be run as movies, depicting the expansion of our universe and the emergence of galaxies about 16 powers of 10 faster than it actually happened. How can we check whether a virtual universe is indeed an accurate resemblance to our real one? The simulation must mimic the observed properties of galaxies today, their characteristic sizes and shapes, the proportions that are disk-like and the proportions that are elliptical, and the way they are clustered. But it must do more. It must match the snapshots that new telescopes are giving us, which tell us what galaxies were like and how they were clustered at earlier times. The light now reaching us from the remotest galaxies set out when they were newly formed, and they look different from present-day galaxies. None has yet settled down into steadily spinning disks, and only a small fraction of their constituent gas has yet turned into stars. Most are small. It took successive mergers and cannibalism by dominant galaxies of their smaller neighbours to build up the large ones that we see today. As a byproduct of early star formation, something even more interesting happens. Some of the gas settles into the centre of the swarm of dark matter particles, contracts under its own gravity, and builds up into a superstar, more than 1,000,000 times heavier than an ordinary star. Such a big object shines so brightly that its nuclear fuel doesn't last long. It ends its life not by exploding, but by collapsing to form a black hole. Thus, once galaxy formation starts, space gets punctured by these holes. Gas continues to fall into them, releasing a power that outshines the rest of the galaxy. These objects are called quasars, or active galactic nuclei, and they are interesting for two reasons. First, they shine more brightly than the galaxies themselves, and therefore serve as probes to illuminate the remote universe. Spectra of quasar light reveal clouds of gas along the line of sight and yield our best evidence to date for the amount of deuterium, an important check, as we have seen, on the Big Bang theory. Secondly, they permit important tests of Einstein's theory of general relativity. The power they emit comes from material that is swirling very close to a black hole, and perhaps even from the spinning hole itself. There is no real chance of getting an actual image of this flow. It would be even more of a challenge than imaging an Earth-like planet around another star. But the radiation it emits is redshifted by the strong gravity, and this would be additional, of course, to the ordinary cosmological redshift. There would also be a large Doppler shift because of the high speed with which the gas swirls around the hole. Red on the side that's moving away, blue from the approaching gas on the other side. From the inferred motions and gravitational fields, we can test whether black holes have the actual properties that Einstein's theory predicts. If one had to summarize in just one sentence what's been happening since the Big Bang, the best answer might be to take a deep breath and say, ever since the beginning, gravity has been moulding cosmic structures and enhancing temperature contrasts, a prerequisite for the emergence of the complexity that lies around us 10 billion years later and of which we are a part. Our universe can thus have evolved from a primordial fireball, uniformly hot, into a structured state containing very hot stars radiating into cold empty space. This sets the stage for increasingly intricate cosmic evolution and the emergence of life. These complexities are the outcome of a chain of events that cosmologists can trace back to an ultra-dense primal medium that was almost structureless. Our view of how cosmic structure emerged is, like the Darwinian view of biological evolution, a compelling general scheme. But as with Darwinism, how the whole process got started is still a mystery. But cosmology is simpler in one important respect. Once the starting point is specified, the outcome is in broad terms predictable. All large patches of the universe that start off the same way end up statistically similar. In contrast, the gross course of biological evolution is sensitive to accidents, climatic changes, asteroid impacts, epidemics, and so forth, so that if the Earth's history were rerun, it could end up with a quite different biosphere. That's why computer simulations of structure formation are so important. Galaxies and clusters are the outcome of gravity acting on initial irregularities. We don't try to explain the detailed pattern, only the statistics, just as an oceanographer aims to understand the statistics of waves, not the details of a wave in a single snapshot at a particular place and time. The starting point is an expanding universe, described by omega, lambda, and q. The outcome depends sensitively on these three key numbers, imprinted we're still not sure how, in the very early universe. The formation of galaxies, clusters and superclusters obviously requires the universe to contain enough dark matter and enough atoms. The value of omega must not be too low. In a universe that contained radiation and very little else, gravity could never overwhelm pressure. And lambda mustn't be so high that the cosmic repulsion overwhelms gravity before galaxies are formed. There must also be enough ordinary atoms, initially in diffuse gas, to form all of the stars in all of the galaxies. But we've seen that something else is needed as well, namely initial irregularities to seed the growth of structure. The number q measures the amplitude of these irregularities or ripples. Why q is about 10 to the minus 5 is still a mystery. But its value is crucial. Were it much smaller or much bigger, the texture of the universe would be quite different and less conducive to the emergence of life forms. If q was smaller than 10 to the minus 5, but the other cosmic numbers were unchanged, aggregation of the dark matter would take longer to develop and would be smaller and looser. The resultant galaxies would be anemic structures, in which star formation would be slow and inefficient, and processed material would be blown out of the galaxy rather than being recycled into new stars that could form planetary systems. If q were even smaller than 10 to the minus 6, gas would never condense into gravitationally bound structures at all, and such a universe would remain forever dark and featureless, even if its initial mix of atoms, dark matter and radiation were the same as in our own. On the other hand, a universe where q were substantially larger than 10 to the minus 5, where the initial ripples were replaced by large amplitude waves, would be a turbulent and violent place. Regions far bigger than galaxies would condense early in its history. They wouldn't fragment into stars, but would instead collapse into vast black holes, each much heavier than an entire cluster of galaxies in our universe. Any surviving gas would get so hot that it would emit intense X-rays and gamma rays. Galaxies, even if they managed to form, would be much more tightly bound than the actual galaxies in our universe. Stars would be packed too close together and buffeted too frequently to retain stable planetary systems. The smallness of q, without which cosmologists would have made no progress, seemed until recently a gratifying contingency. Only now are we coming to realize that this isn't just a convenience for cosmologists, but that life couldn't have evolved if our universe didn't have this simplifying feature. The Big Bang theory has lived dangerously for more than 30 years, but it has survived. The grounds for extrapolating back to the stage when our universe had been expanding for a second, when the helium began to form, deserve to be taken as seriously as, for instance, inferences from rocks and fossils about the early history of our Earth, which are equally indirect and less quantitative. Perhaps we can deepen our understanding and even explain the key cosmic numbers by extrapolating still further back, not just into the first second, but into the first tiny fraction of a second. We can confidently go back a bit closer to the Big Bang, but not much. For the first millisecond, we are less sure of the physics, because everything would then have been denser than a neutron star. Very hot and dense conditions can be simulated on a microscopic scale by experiments that crash together very energetic particles. But there are limits to how far back even this technique can take us. Not even a giant Large Hadron Collider, being built at CERN in Geneva, will achieve the energies that all the particles in the Big Bang had during the first 10 to the minus 14 seconds. Many crucial features of our universe could have been imprinted when the cosmic clock was reading 10 to the minus 35 seconds, or even less. In these contexts, each factor of 10 on the cosmic clock in the age of the universe, each extra zero after the decimal point, or each power of 10, is likely to be equally eventful and should count equally. So the leap back from 10 to the minus 14 seconds to 10 to the minus 35 seconds is then bigger, in that it spans more factors of 10 than the time span between the 3-minute threshold when helium was formed and the present time, 3 times 10 to the 17 seconds, or 10 billion years. In this perspective, there is plenty of action at even earlier stages. Right back at the beginning, the mysteries of the cosmos and the microworld overlapped. To probe these mysteries, we need to relate gravity, the dominant force on large scales, to the other forces that govern individual particles. This is still unfinished business. But the various forces and particles of the subatomic world are now seen to fall into a pattern. Early in the 19th century, Michael Faraday realized that electricity and magnetism were intimately linked. A moving magnet generated electric currents, a moving electric charge, conversely, created a magnetic field. In 1864, James Clerk Maxwell codified Faraday's discoveries into a famous set of equations, which expressed how a changing electrical field generates a magnetic field, and vice versa. In empty space, these equations have solutions where the electric and magnetic fields oscillate. This is what light is. It's a wave of electric and magnetic energy. This left just two distinct forces: electromagnetism, perceived as a single force, and gravity. Even Faraday yearned for a unification between gravity and electromagnetism, although he realized that it was premature. 100 years on, Einstein spent his later years seeking a deep connection between these two forces. This was still a vain quest. Indeed, we now realize that it was doomed, because Einstein didn't then know about the short-range forces that govern atomic nuclei, the strong or nuclear force that binds protons and neutrons together, and the weak force important for radioactive decay and neutrinos. In the opinion of his outstanding biographer, Abraham Peiss, Einstein might as well have gone fishing for the last 30 years of his life. The challenge is now to unify four forces, the three that govern the microworld: electromagnetism, the nuclear force, and the weak force, and the force of gravity. The first modern step towards this unification was associated with the names of Sheldon Glashow and Steven Weinberg in the United States, Gerhard 't Hooft in Holland, and the Pakistani physicist Abdus Salam. Their work showed that the electric and magnetic forces, unified by Maxwell, are themselves linked to an apparently quite different force, the so-called weak force. These forces would have been the same in the very early universe. They acquired distinctive identities only after the universe had cooled below a critical temperature of about 10 to the 15 degrees. The biggest accelerators can simulate these temperatures, and Salam and Weinberg were vindicated when experiments at CERN discovered new particles that they had predicted. In the 1950s and 1960s, so many new kinds of particles were discovered, supplementing the familiar electrons, neutrons, and protons, that there seemed a risk that particle physics would become like stamp collecting. But patterns were discerned. The subatomic particles could be grouped into families, rather as the atoms in the periodic table fall into periods and groups. The so-called Standard Model that emerged in the 1970s has brought impressive order into the microworld. The electromagnetic and weak forces have been unified, and the strong or nuclear forces have been interpreted in terms of quarks, held together by another kind of particle called a gluon. But nobody has taken this as the final word. The number of elementary particles remains bewilderingly large, and the equations still involve numbers that have to be determined by experiments and can't be derived from theory alone. In particular, the gluon interpretation does not pin down the strength of nuclear forces, crucially manifested in our basic number 0.007. The next goal after unifying the electromagnetic and weak forces is to bring in the nuclear force, and thereby achieve a so-called grand unified theory of all the forces governing the microphysical world. Although these theories are still not grand enough to include gravity, which poses a still greater challenge. A stumbling block is that the grand unification is thought to occur at a temperature of 10 to the 28 degrees. This is a million times higher than experiments can presently reach, and to achieve the requisite energies would need an accelerator far bigger than our solar system. It's hard, therefore, to test these theories on Earth. Their distinctive consequences in our low-energy world are vestigial. For instance, protons, the main ingredient of all stars and planets, would very slowly decay, an effect that could be important in the remote future but is insignificant now. Everything, however, would have been hotter than 10 to the 28 degrees for the first 10 to the minus 35 seconds. Perhaps the early universe was the only place where the requisite temperature for unifying the forces could ever be reached. This experiment shut down more than 10 billion years ago, but did it leave fossils behind? It seems that it did. The vast scale of the universe and the fact that it is expanding at all may be determined by what happened in those brief initial instants. Two fundamental questions about our universe are, why is it expanding, and why is it so big? We can trace out what happens during the expansion, and we can extrapolate right back to the first few seconds and corroborate this with the helium and deuterium abundance. But the so-called Big Bang theory is really a description of what happens after the Big Bang. It says nothing about what set up the expansion in the first place. Another puzzle is, why does our universe have the overall uniformity that makes cosmology tractable, while nonetheless allowing the formation of galaxies, clusters and superclusters? And, still further, what imprinted the physical laws themselves? One basic mystery is why our universe is expanding after 10 billion years, with omega still not too different from a value of 1. Our universe has neither collapsed long ago, nor is it expanding so fast that its kinetic energy has overwhelmed the effect of gravity by many powers of 10. This requires omega to have been tuned amazingly close to unity in the early universe. What made everything start expanding in this special way? Why, when we observe remote regions in opposite directions, do they look so similar? Or why is the temperature of the microwave afterglow almost the same all over the sky? These mysteries would be solved if all parts of our present universe had synchronized and coordinated themselves very early on and then accelerated apart. This is the key postulate of the so-called inflationary universe theory. The American physicist Alan Guth put forward this idea in 1981. As so often happens in science, there were several precursors, especially the theories of Alex Starobinsky and Andrei Linde in the Soviet Union and Katsumoto Sato in Japan. But Guth made the arguments clear enough to convince most of us that this was indeed a crucial insight. According to the inflationary universe theory, the reason why our universe is so big and why gravity and expansion are so closely balanced lies in something remarkable that happened very early on, when our entire observable universe was literally of microscopic size. At the colossal densities that then prevailed, a cosmic repulsion, rather like an enormously strong lambda, came into play and overwhelmed ordinary gravity. The expansion was kicked into overdrive, leading to runaway acceleration, so that an embryo universe could have inflated, homogenized, and established the fine-tuned balance between gravitational and kinetic energy. All this is supposed to have happened within about 10 to the minus 35 seconds of the Big Bang. The conditions that prevailed back then are far beyond what we can test experimentally, and the details are therefore speculative. We can nonetheless make guesses consistent with other physical theories and with what we know about the later universe. The idea behind the inflation theory is compellingly attractive because it seems to show how an entire universe could evolve from a tiny seed. This is deemed to have happened because the expansion is exponential. It doubles, and then doubles again. Mathematical formulae, unless they're very long and complicated indeed, generally don't yield huge numbers. The only natural way for a modest number to generate a gigantic one, such as 10 to the 78, the total number of atoms in our observable universe, is if it is in the exponent, so that it tells us how many times the size doubles. Each time a sphere doubles its radius, its volume goes up by a factor of 8. Only 100 of these doublings will be needed in order to reach a number like 10 to the 78. This is just what is proposed as happening during the inflationary phase of our universe. The fierce repulsion that drove inflation must then have switched off, allowing the universe, having by then enlarged enough to encompass everything we now see, to embark on its more leisurely expansion. This transition converted the huge energy latent in the original vacuum into ordinary energy, generating the heat of the fireball and initiating the more familiar expansion process that has led to our present universe. The concept of inflation has been boisterously debated, but at the moment it offers the only credible explanation for why our universe is so large and so uniform. It suggests why the universe is expanding at such a seemingly fine-tuned rate, so that it could heave itself up to dimensions of 10 billion light-years. If a wrinkled surface is stretched by a huge factor, then the curvature reduces until any deviations from flatness are imperceptible. The analogue of flatness in cosmology is an exact balance between negative gravitational energy and positive expansion energy. This is the firmest generic prediction of inflation. So is it fulfilled? The simplest kind of flat universe is one in which omega is exactly unity. The evidence that atoms and dark matter contribute only 0.3 of the critical density seemed at first sight to be a setback. Theorists therefore seized enthusiastically on the claim that the expansion is accelerating, because the energy associated with the number lambda must then be added in. Our universe then seems indeed to be flat. The mix of stuff that makes up the critical density is 4% atoms, about 25% dark matter, and the rest is the vacuum, or lambda, itself. This evidence of flatness is moderately encouraging. It at least motivates us to seek further tests, especially diagnostics that might reveal details of what happened during inflation. Most detailed ideas about the ultra-early universe have a short shelf life. The first 10 to the minus 35 seconds is still rather uncertain. Along with the fluctuations that develop into galaxies and clusters, the inflation is thought to generate gravitational waves, oscillations in the fabric of space itself, crisscrossing the universe at the speed of light. Objects encountered by such waves feel a gravitational force that pulls them first one way and then the other. They shake slightly as a result. The effect is minuscule, and its detection in reality poses a formidable technical challenge. It might seem counterintuitive that an entire universe, 10 billion light-years across, can have emerged from an infinitesimal speck. What makes this possible is that, however much inflation has occurred, the universe's net energy can still be zero. Everything has energy mc squared, according to Einstein's famous equation. But everything also has negative energy because of gravity. We need energy to escape from Earth's gravity. Down on the Earth's surface, we therefore have an energy deficit compared to an astronaut in space. But the deficit, technically called gravitational potential energy, due to everything in the universe added together, could amount to minus mc squared. In other words, the universe makes for itself a gravitational pit so deep that everything in it has a negative gravitational energy that exactly compensates for its rest mass energy. So the energy cost of inflating our universe could actually be zero. The most important implication of inflation is that it grandly and dramatically enlarges our perspective on the universe. To explain the universe that we see, there must have been enough inflation to account for everything within range of our telescopes. But that's just a minimum. It may take a long time to stop the inflation once it has started. Indeed, most versions of the theory suggest that the number of doublings should be far more than is needed to account for our observable universe. We have imagined a succession of views of our universe, each taken 10 times further away than the last. 25 frames took us to the limits of our present vision, starting from the everyday human scale. This limit is set, essentially, by how far light has been able to travel in the 10 billion years or so since the first galaxies formed. But inflation theorists envisage a universe so much larger that it would take millions of frames, each a leap by a factor of 10, to reach any edge. This stupendous expanse of space is, to me at least, impossible to grasp. The time before light reaches us from the edge is then a number of years, written not just with 10 zeros, nor even with 100, but with millions of zeros. But this isn't all. Even this colossal universe, whose extent requires a million-digit number to express it, may not be everything there is. It is the outcome of just one episode of inflation, but that episode, that Big Bang, may itself be just one event in an infinite ensemble. Indeed, this is a natural consequence of the eternal inflation, espoused especially by the Russian cosmologist Andrei Linde. According to this scenario, which requires specific, though still speculative assumptions about the physics at extreme densities, the cosmos may have had an infinite past. Patches where inflation doesn't end always grow fast enough to provide the seeds for other Big Bangs. There are variants on these speculations in which an episode of inflation could be triggered inside a black hole, creating new domains of space and time disjoint from our own. Our space has 3 dimensions. There are points, 0 dimensions, lines, 1 dimension, surfaces with 2 dimensions, and solid objects with 3 dimensions. But there the sequence stops, even though mathematically we can imagine a kind of space that has more. What is special about the number 3? One consequence of a 3-dimensional world is that forces like gravity and electricity obey an inverse square law, such that the force from a mass or charge is 4 times weaker if you go twice as far away. Michael Faraday, in his pioneering studies of electricity, had a graphic and essentially correct way to understand this. He envisaged lines of force sprouting from every charge or mass, the strength of the force depending on how concentrated the lines are. At a distance r, the lines are spread out over an area proportional to r squared. At larger distances, the force is consequently diluted, its strength depending inversely on r squared. But the area of a four-dimensional sphere would vary in proportion to r cubed. It would be 8, not just 4 times larger, if r doubled in value. Faraday's argument would then imply an inverse cube law. As Newton realized, the trajectories of planets are controlled by a balance between the effects of gravity, tending to pull them inward, and the centrifugal effect of their motion. Orbits in our solar system are stable, in the sense that a slight change in the planet's speed would only nudge its orbit slightly. But this stability would be lost if gravity followed an inverse cube or steeper law, rather than one based on inverse squares. An orbiting planet to be slowed down even slightly would then plunge ever faster into the Sun, rather than merely shift into a slightly smaller orbit, because an inverse cube force strengthens so steeply towards the center. Conversely, an orbiting planet to be slightly speeded up would quickly spiral outwards into darkness. For similar reasons, atoms would be impossible in a universe ruled by an inverse cube law, because there would be no stable orbits for electrons. There is therefore a problem with more than 3 spatial dimensions. Could we then live in a world where there were less than 3? The best argument here is a very simple one. There are inherent limitations on complex structures in flat land. It is impossible to have a complicated network without the wires crossing, nor can an object have a channel through it, a digestive tract, for instance, without dividing into 2. And the scope is even more constricted in a one-dimensional line land. These are just the most obvious reasons, and mathematicians have discovered others, as to why we shouldn't be surprised that we find ourselves living in 3-dimensional space. As an anonymous graffiti writer put it, time is nature's way of stopping things happening all at once. Time is, of course, a 4th dimension that we experience. To locate an event, we need 4 numbers. 3 spatial coordinates to describe where it happened, and a 4th to tell us when. But time is different from the other 3 dimensions, insofar as we seem to be dragged only one way in it, forward. In the other 3, we can move in any direction. Our universe is thus best described as 3 + 1 dimensional. Einstein taught us that space and time are linked, and that the rate at which time passes is elastic, being dependent on how a timekeeper is moving, and whether or not that timekeeper is near to a large mass. But Einstein's ideas retain the distinction between time and space, between what's out there in space and what lies in the past or future. An arrow of time points insistently from the past towards the future. The asymmetry between past and future is so ingrained in our experience that few, except for some philosophical physicists, pause to ponder the conundrum this poses. It is perplexing because no such asymmetry is built into the basic laws governing the microworld. The world changes irreversibly, even though the underlying laws are indifferent between past and future. Time poses mysteries on which there is absolutely no consensus. The physicist Julian Barber conducted an informal poll among experts on this question. Do you believe time is a truly basic concept, or can it be derived from more primitive notions, rather as, for instance, an object's temperature derives from the agitated motions of its constituent atoms? Responses to Julian Barber were quite evenly divided, with a slight majority favouring the view that time would eventually be interpreted in terms of something deeper. Space and time certainly have a complicated structure. We know that space is punctured by black holes, millions within our galaxy, even bigger ones in the centres of other galaxies, in which time and space are intertwined. But these complications are restricted to regions that are local in a cosmological perspective. The near uniformity of our universe on scales larger than superclusters suggests that the geometry of space is smooth and simple on the scale of our present horizon. So also does the fact that the background microwave radiation has almost the same temperature over the whole sky. But beyond the horizon set by the finite speed of light, observations tell us little. Space could be wrapped in a complicated way. There could even be changes in the number of dimensions. but we shall never have more than indirect intimations of what happens beyond the range of any telescope. What about ultra-small scales? Here, our simple concepts certainly break down. Indeed, we may need to grapple with very complicated ideas involving extra dimensions in order properly to understand the particles, the forces, and our cosmic numbers. Space seems a smooth continuum, but that is only because our experience, and even our most sophisticated experiments, are too coarse to probe the very fine scale on which any graininess will be manifest. We don't know the detailed microstructure of space and time, but fine-scale detail could only be probed by radiation with wavelengths still shorter than that scale. Light consists of waves a millionth of a meter long, and nothing smaller than that can be imaged with an ordinary optical microscope. To probe sharper detail requires still shorter wavelengths, or else some other technique such as an electron microscope. But, according to the quantum theory, shorter wavelengths come in more energetic quanta, or packets of energy. The basic quantum of energy is measured by Planck's constant, a number named after the great physicist Max Planck, who pioneered the idea of quantization a century ago. Up to a point, we can probe ever finer detail by using more and more energetic quanta associated with ever shorter wavelengths. But there's a limit. This limit arises when the requisite quanta are such extreme concentrations of energy that they collapse into black holes. This happens at the Planck length, which is about 10 to the 19 times smaller than a proton. Quanta with this tiny wavelength each carry as much energy as the rest mass of 10 to the 19 protons. Light takes about 10 to the minus 43 seconds to traverse this distance, and this Planck time is the shortest time interval that can ever be measured. So even space and time are subject to quantum effects. Some theorists are more willing to speculate than others, but even the boldest acknowledge the Planck scales as an ultimate barrier. We can't measure distances smaller than the Planck length. We can't distinguish two events or decide which came first when the time interval between them is less than the Planck time. These scales are smaller than atoms by just as much as atoms are smaller than stars. There's no prospect of any direct measurement in this domain. It would require particles with energies 1,000,000 billion times higher than could be produced in the laboratory. The two great pillars of 20th century science are quantum mechanics, crucial in the microworld, and Einstein's theory of gravity, which does not incorporate quantum concepts. But we have no single framework that reconciles and unifies them. This lack doesn't impede the progress of terrestrial science, nor indeed the advance of astronomy, because most phenomena involve either quantum effects or gravity, but not both. Gravity is negligible by our huge number n in the microworld of atoms and molecules, where quantum effects are crucial. Conversely, quantum uncertainty can be ignored in the celestial realm of planets, stars, and galaxies, where gravity holds sway. But, right back at the beginning, quantum vibrations could shake the whole universe. Conversely, gravity could be important on the scale of a single quantum. This happens at the Planck time. To understand the first instance after the Big Bang, or the space and time near the so-called singularity inside black holes, we need a unification of quantum theory and gravity. Ordinary intuition breaks down at speeds approaching that of light and near black holes. And it breaks down, too, at the extreme conditions of the very early universe, and on microscales close to the Planck length. We must then jettison cherished common sense notions of space and time. Black holes may be appearing and disappearing. Space-time on this tiny scale may have a chaotic foam-like structure with no well-defined arrow of time. The fluctuations may spawn new domains that evolve into separate universes. Space may have a kind of lattice structure, or be knotted rather like chainmail. Time may become like space, so that in a sense there is no beginning of time. The only other arena for quantum gravity is the central singularity within black holes, shrouded within the horizon. A theory that has no manifest consequences except in such exotic and inaccessible domains is hard to check. Several approaches are being followed, but there is no consensus yet about which is the right one. The most ambitious and encouraging approach seems to be superstring theory, which leapfrogs directly to a unified theory of all the forces and yields quantum gravity almost as a bonus. Superstring theory can, its proponents claim, incorporate the three forces that govern the microworld, as well as accounting for the elementary particles, quarks, gluons, etc. The existence of gravity is actually an essential ingredient of the theory, rather than an extra complication. Its key idea is that the fundamental entities in our universe are not points, but tiny string loops, and that the various subnuclear particles are different modes of vibration, different harmonics of these strings. The strings have the scale of the Planck length. Moreover, these strings are vibrating not in our ordinary 3+1 dimensional space, but in a space of 10 dimensions. In superstring theory, each point in our ordinary space is a complicated geometrical structure in 6 dimensions, a kind of origami wrapped up on the scale of the Planck length. All physical theories involve equations and formulae that render the technicalities, though not fortunately the key ideas, opaque to the non-specialist. But generally the mathematics has already been worked out and can be taken off the shelf by the physicists. For instance, the geometrical concepts that Einstein used in his theory of curved space-time had all been developed in the 19th century. So also was the mathematical language that was deployed to describe the quantum world. But superstrings pose questions that still baffle mathematicians, and as an unbridged gap between the intricate complexity of 10-dimensional string theory and any phenomena we can observe or measure. Nonetheless, there are specific reasons for being optimistic about superstrings. One is that Einstein's theory of general relativity, which interprets gravity as curvature in 4-dimensional space-time, is inescapably built into superstring theory. The long-sought synthesis between gravity and the quantum principle should then naturally emerge. In our universe, intricate complexity has unfolded from simple laws. But it's not guaranteed that simple laws permit complex consequences. Indeed, we've seen that different choices of our 6 numbers would yield a sterile universe. There are various ways of reacting to the apparent fine-tuning of our 6 numbers. One hard-headed response is that we couldn't exist if these numbers weren't adjusted in the appropriate special way. We manifestly are here, so there's nothing to be surprised about. Many scientists take this line, but it leaves me unsatisfied. I am impressed by a metaphor given by the Canadian philosopher John Leslie. Suppose you are facing a firing squad. 50 marksmen take aim, but they all miss. If they hadn't all missed, you wouldn't have survived to ponder the matter. But you wouldn't just leave it at that. You'd still be baffled and would seek some further reason for your good fortune. Others adduce the tuning of the numbers as evidence for a beneficent creator who formed the universe with the specific intention of producing us. This is a so-called argument from design for God's existence. Variants are espoused by eminent scientist theologians, such as John Polkinghorne. He writes that the universe is not just any old world, but it's special and finely tuned for life, because it is the creation of a creator who wills that it should be so. If one doesn't accept the providence argument, there is another perspective which, though still conjectural, I find compellingly attractive. It's that our Big Bang may not have been the only one. Separate universes may have cooled down differently, ending up governed by different laws and defined by different numbers. This may not seem an economical hypothesis. Indeed, nothing might seem more extravagant than invoking multiple universes. But it opens up a new vision of our universe as just one atom selected from an infinite multiverse. This multiverse concept, though speculative, is a natural extension of current cosmological theories, which gain credence because they account for things that we do observe. André Linde and others have already shown us that some sets of assumptions, consistent with everything else we know, yield many universes that sprout from separate Big Bangs into disjoint regions of space-time. If there are indeed many universes, the next question is, how much variety do they display? There is a possibility that each might evolve in a distinctive way, being characterized by a different set of numbers from those that are so crucial molding our own universe. Universes could have different values of omega, which fixes the density and how long their cycle lasts if they recollapse, and Q, which measures how smooth the universe is and so determines what structures emerge in it. In sum, gravity could be so overwhelmed by the repulsive effects of the vacuum energy lambda that no galaxies or stars can form. Or the nuclear forces may be outside the range close to 0.007 that allows elements like carbon and oxygen to be stable and to be synthesized in stars. There would then be no periodic table and no chemistry. And some universes might be just too small and simple to permit any internal complexity at all. I have highlighted one basic number, n, that is exceedingly large. Its size reflects the weakness of gravity. Very large numbers of particles have to gather together before gravity becomes important, as it does, for instance, in stars, gravitationally bound fusion reactors. It's a straightforward consequence of their size that stars have lifetimes that are enormously long, allowing time for photosynthetic and evolutionary processes to unfold on suitable planets in orbit around them. The recipe for any interesting universe must include at least one very large number. Clearly, not much could happen in a universe that was so constricted that it contained few particles. Every complicated object must contain a large number of atoms. To evolve in an elaborate way, it must also persist for a long time. But an abundance of particles in a long stretch of time are not in themselves sufficient. Even a universe as large, long-lived and stable as ours could contain just inert particles of dark matter, either because the physics precludes ordinary atoms from ever existing, or because they all annihilate with exactly equal numbers of antiatoms. If there were indeed an ensemble of universes, described by different cosmic numbers, then we'd find ourselves in one of the small and atypical subset where the 6 numbers permitted complex evolution. The seemingly designed features of our universe shouldn't then surprise us, any more than we are surprised at our particular location within our universe. We find ourselves on a planet with an atmosphere, orbiting at a particular distance from its parent star, even though this is really a rather special and atypical place. A randomly chosen location in space would be far from any star indeed. The view that our 6 numbers are accidents of cosmic history is still no more than a hunch, but it could be firmed up by advances in our understanding of the underlying physics. More importantly for its standing as a genuine scientific hypothesis, it's vulnerable to disproof. We would need to seek a different interpretation if the numbers turned out to be even more special than our presence requires. Elucidating the ultra-early universe and clarifying the concept of the multiverse are challenges for the new century. These challenges look less daunting if we look back at what has been achieved during the 20th century. 100 years ago, it was a mystery why the stars were shining. We had no concept of anything beyond our Milky Way, which was assumed to be a static system. In contrast, our panorama now stretches out for 10 billion light-years, and its history can be traced back to within a fraction of a second of the beginning. This progress is possible only because of the contingency, in principle remarkable, that the basic physical laws are comprehensible and apply not just on Earth, but also in the remotest galaxies, and not just now, but even in the first seconds of our universe's expansion. Only in the first microsecond of cosmic expansion and deep inside black holes do we confront conditions where the basic physics remains unknown. It remains a fundamental challenge to understand the very beginning. This must await a final theory, perhaps some variant of superstrings. Such a theory would signal the end of an intellectual quest that started with Newton. It would deepen our understanding of space, time and the basic forces, as well as elucidating the ultra-early universe and the centers of black holes. This goal may be unattainable. There could be no final theory, or if there is, it could be beyond our mental powers to grasp it. But even if this goal is reached, that would not be the end of challenging science. As well as being a fundamental science, cosmology is also the grandest of the environmental sciences. It aims to understand how a simple fireball evolved into the complex cosmic habitat we find around us. How here on Earth, and perhaps in many biospheres elsewhere, creatures evolved that are able to reflect on how they emerged. There is no chance that our finite observable universe, even though it extends 10 billion light-years around us, can play out all its potentialities. This is because any estimate of how many different chains of events could happen quickly runs into even vaster numbers than we've encountered so far. The number of different chess games, even after only 3 moves by each player, is about 9 million. There are far more 40-move games than the 10 to the 78 atoms within our horizon. Even if all the material in the universe were made into chessboards, most possible games would never be played. And the range of options in a board game is obviously minuscule compared to the variety allowed in nature. Even simple inanimate systems are generally too chaotic to be predictable. Newton was actually lucky to find in planetary orbits one of the few aspects of nature that are highly predictable. Any biological process involves tremendously more variety, more branch points at every stage as complexity unfolds, than a game of chess. If there were millions of Earth-like planets in each galaxy that all harbored life, each one would be distinctive. This perspective should caution us against scientific triumphalism, against exaggerating how much we'll ever really understand of nature's intricacies. A theme of this book has been the intimate links between the microworld and the cosmos. Our everyday world, plainly moulded by subatomic forces, also owes its existence to our universe's well-tuned expansion rate, the process of galaxy formation, the forging of carbon and oxygen in ancient stars. A few basic physical laws set the rules. Our emergence from a simple Big Bang was sensitive to 6 cosmic numbers. Had these numbers not been well-tuned, the gradual unfolding of layer upon layer of complexity would have been quenched. Are there an infinity of other universes that are badly tuned and therefore sterile? Is our entire universe an oasis in a multiverse, or should we seek other reasons for the providential values of our 6 numbers?